Hello friends, myself Shriram Korde. I welcome you all to Deep Learning for Computer Vision. So when we talk about deep learning for computer vision, one needs to understand or have a question, what's the intuition behind image data processing and feature extraction? The answer is computer vision. So when we talk about computer vision, it's an area of deep learning that deals with image recognition and image classification. So having said this, there are computer vision models which accomplish such tasks. The examples are facial recognition, identifying a breed of a pet, then at times identifying a tumor from CT scan. Such examples are endless. So before we understand the course content also, one needs to understand how do computers see images. So computers don't see images the way in which humans do. They only understand numbers. So having said this, is deep learning for computer vision a success? The answer is big yes. The success of deep learning methods has done a revolution in the field of computer vision, and it's a pretty recent success. So because of that, it's making new development increasingly closer to deployment in the field, which basically benefits end user. So having understood or having said that the computer vision happens to be one of the important area when it comes to deep learning, that is deep learning for computer vision is what the course is about. So one needs to understand now what are the course content, that means what's there for me. So as a part of this tutorial series, one will understand the introduction to deep learning, and that introduction will be in quite a depth. Then one will understand the gradient descent things as well as the mathematics behind the gradient descent. Then you will go through artificial neural network. Then you will understand the functional API, which is again one of the advanced topic. Then you will understand convolution, then convolutional neural network, then how one makes use of OpenCV for some of the applications. Then you will understand the models like VGG16. Then how do we carry out image segmentation? Then what's the model which is ResNet, and it's one of the latest model. Then having understood the ResNet, one is ready to understand the exception net, which is again a very latest model. So when you understand all these models, then you also will go through how typically the cognate learn. That means suppose if I take an example of exception, then one will visualize or how typically visualize of cognates filtering or the filters related to cognates happen. So that also is covered. So when we talk about these topics, the question is what are we going to use? That means what is my programming environment or development environment? So it's going to be Keras oblique TensorFlow, and you are going to use 2.x version. So it will be 2.8 version. Apart from that, obviously we are going to rely on Python. So these are some of the contents or the broad points or the broader areas when it comes to this particular course. I hope you will find these contents interesting and you will go into each topics in depth. The focus of this course is you understand the background or the intricacies which are part of various models, like when it comes to say ResNet, image segmentation, exception and all that. So considerable time has been dealt on models so that you understand this topic of deep learning for computer vision thoroughly. Thank you. Hello friends, Myself Shri Korde. Welcome you all to Deep Learning tutorial series. As part of this video, we are going to understand deep learning basics. So when I say basics, then the question comes that what is deep in deep learning? Why? Because there is a name called as deep learning. So that means what is deep in deep learning? Then what do you mean by learning itself? So there are so many such questions which one needs to understand. So let's try to get into these questions and also in that process understand deep learning topic. So as part of this video, we are going to concentrate on AI, ML and DI. Then we'll talk a little bit about machine learning. Then we'll talk about what is deep in deep learning. Then what do you mean by learning in deep learning? And then what's next? That means what one should learn as part of deep learning curriculum. So let's get into it now. So once again, welcome you all. So AI, ML and DL. So this happens to be a very commonly seen diagram. That means artificial intelligence, machine learning and deep learning. So from the diagram, it's pretty obvious that artificial intelligence encompasses machine learning as well as deep learning. So having said this, so that means when somebody is trying to say that okay, I'm going to do a course on machine learning or I'm trying to do a course on deep learning, and probably now you know what exactly it means by that. So let's now understand this aspect more. So what is artificial intelligence? So essentially it's a general field that encompasses machine learning and deep learning. So when was this field used or why typically people use this field? So this is suitable to solve well-defined logical problems. The example can be like I can use artificial intelligence type of approach for playing chess. So when I say that I would like to use such an approach, that means now I know that there is going to be explicit rules are there, and using those rules I can develop a program where I can play a play chess with computer. However, there are cases where one needs to solve complex problems. The examples are like when I want to carry out something like image classification, speech recognition, and language translation. Now, when I say image classification, then somebody might give me images of say flowers, various types of flower. Somebody may give you images of various types of animals like dog, cat, horse, elephant and all that. Similarly, when it comes to speech recognition, if people give me the samples of speeches, then one should be able to tell to a certain extent that okay, this speech corresponds to such and such person, or for that matter even recognize what that speech is trying to convey. So all these are examples of where you basically want to do some complex activity and where typically AI may not be able to solve. So to solve such problems which essentially are intractable to figure out rules, there is a new approach, and that new approach which arose is essentially machine learning. So in that process now the question comes, could a computer go beyond? So what do you mean by computer go beyond? That means whatever as a human being we know, then can it go beyond that? So let's say example is what we know how to order it to perform and learn on its own how to perform a specified task. So now this particular thing, what we know how to order it to perform and learn on its own how to perform a specific task. So could a computer go beyond such aspect? Then could a computer surprise us? Like rather than programmers crafting data processing rules by hand, could a computer automatically learn these rules by looking at the data? That means now we are talking about a case where computer on its own is able to go beyond something where we just tell, okay, we just order it to perform, and then we basically ask him, okay, you basically do such and such task. So instead of that, can a computer automatically learn these rules by looking at the data? And that's where machine learning comes into picture. So here you have a input data as well as the answers expected from the data. That means you essentially have to give input as the data itself, and what do you expect as an answer, that also happens to be input, and then comes the rules, that means the outcome is the rules. So how do I basically depict it? So this is the way typically classical programming looks like. The people who are habituated to doing say C programming, or for that matter C++ programming, or in general any programming, say scripting programming and all that, and normally they are habituated to think like this. Like suppose if someone asks me to write a program to arrange say n numbers or 10 numbers in ascending order, then what am I going to do? I will have a rules of say checking. Then there are 10 numbers which basically are data, and then answer is like accordingly I am going to get output, which essentially will be say ascended numbers or the numbers in the ascending orders. So this is what typically we consider it as a classical programming. Now if one needs to go beyond this, and that's where the machine learning fits in. So here now you have the data itself, and for that corresponding data you also tell to machine this is the answer. Now from this approach, then the outcome is rules. So now you can see very clearly what is the definition of machine learning. That means you have data as an input, you have answer as an input, and then outcome is the rules. So machine learning essentially is trained. That means now when we are talking about machine learning, the machine learning system itself is trained. That means now it's going to find statistical structure in the data or in the examples. When we say examples, that means the input data. Then it's going to apply those rules to the new data to produce the answers. Then ML model finds. Now when you talk about all this, typically the model word is used, and we are anyway going to understand it later. So the ML model or the ML system finds appropriate representation of the input within a predefined space of possibilities using guidance when required from a feedback signal. But here let's try to simplify this, or let's try to understand it. When we say that within a predefined space of possibilities, that means let's say that there is a car manufacturer in your country. So for example in India there is a car manufacturer say by name Hyundai. Now Hyundai is going to make multiple models. Now if you basically give those picture objects for training to recognize a car, and let's say on new data, let's say now you happen to give a Toyota car, or say you happen to give a Honda car, then in that case, because your training has happened on various Hyundai cars model, then obviously the when you give a Honda car or a Toyota car, then in that case it's not going to exactly say that okay this is what it is, but it's going to match to a design, or it is going to match to a figure which was looking more like say so the Honda car, probably Honda City or whatever the car that you try to give as a new input, and it's going to do that mapping within the predefined space of possibilities. That means whatever you have trained, it knows that these are the possibilities. So that's what essentially it means. So when you now speak about machine learning, so we basically talk about training. That means you need to find the statistical structure in the data or the examples, then you apply the rules to the new data or the unknown or unseen data, and then you basically find the appropriate, that means these models are going to now find the appropriate representation for that those particular new data. So now let's get into the deep learning. Having understood the concept about machine learning, now let's try to get into little bit about deep learning. So when we talk about deep learning, so one needs to understand what it is. So it's a specific subfield of machine learning, and that's what the first diagram that I showed you, oval diagram, was trying to show that. Then it's a new take on learning representations from data. Now here the key thing to understand is we are talking about learning representations from data. Now this word is very important, learning representation. So this representation word is very important, and then it's going to have a layered approach. That means you have layers of book. That means you can keep book one above another, books one above another. On the similar lines, when we talk about deep learning, it's going to have different layers. That means layer 1, layer 2, like that you are going to have multiple such layers. And the key point here is that learning representations from the data. So what is now deep in the deep learning? So that one now needs to understand, and now we have reached that exact question that I have started with this discussion. So the deep in deep learning. So what it is? So it's not a reference to any kind of deeper understanding achieved by layered structure. So what does it do now? So it puts an emphasis on learning successive layers of increasingly meaningful representation. So now that word representation plays a very important role. That means now you have layers. However, the emphasis is on learning successive layers of increasingly meaningful representation. That means now these layers are going to help you understand or help you decipher the input that you are trying to feed to a system, and using those layered structure where you are going to have increasingly meaningful representation, you are able to tell the answer or you are able to predict the answer. So essentially now it stands for this idea of successive layers of representation. Then there are other names that typically people use in literature, like layered representation learning. Why? Because I have told you like it's a layered approach, and then I also told you to concentrate on the word learning representation, and that's why the other name is layered representations learning. At times people also use hierarchical representation learning. Why? Because when we talk about layer by layer, then essentially we are talking about hierarchical representation learning. So let's now understand layered representation. So layered representations are learnt via models called as neural networks. So initially we have used this word model earlier. So when we have used this model word, so essentially we deal with right now in the context of deep learning as a neural networks. Then the layers are stacked on top of each other. Neural network is a reference to neurobiology. That means it has drawn inspiration from our understanding of the brain. Now please understand this point very clearly. Neural network is a reference to neurobiology. That means there is an inspiration that has been drawn from human beings or our understanding of the brain. It's an our understanding, please understand it. So that means now people will start thinking, or you will start thinking, okay, now it's going to model brain. So does it model brain? That's the question. So DL models, when we talk about the models in deep learning, that is neural network model, they are not models of the brain. However, they are inspiration from our understanding of the brain. Now why do I say that? Why? The reason is because there is no evidence which says that brain implements anything like the learning mechanism used in modern deep learning models. Why? Because I just have told you like it's a learning representations within the different layers. So there is no evidence that brain learns like this. However, the overall inspiration is basically drawn from our understanding of the brain, and that's why typically it is there is a reference given to neurobiology. So let's understand it now. So what it is? So let's continue. So it is a mathematical framework for learning representations from data. So now the key point here is learning representation. So I have already told you concentrate on learning representation. So now to add to it now, we are talking about a mathematical framework. So mathematical framework for learning representations from data. Let's take an example. Let's say you have a handwritten image. Now such images are available. In case you do Google and just figure out handwritten images, then you are going to get. They are also available as part of data sets, as part of Keras or TensorFlow. So let us say that the input image here is 5 digit, which is some handwritten digit. So now you basically feed such an image to to layer 1, then it goes to layer 2, then layer 3, layer 4, and then you basically the system has to tell whether this digit corresponds to 0 or whether it corresponds to 1 or 2, like that till 9. Obviously we should expect the system to tell that the output is or the input digit that has been given is essentially a handwritten digit 5. That means the final output should say it's a 5 digit. So that's what we have said, a layer 1, layer 2, layer 3. So increasingly meaningful, or there is a representations that is happening with respect to layered approach. So let's see it in more details. So let us say that you have a handwritten image 4. Now you feed it to layer 1, which is essentially the input layer. and then there are intermediate layers like layer 2, layer 3, layer 4, and then finally there is the outcome. That means if such an handwritten digit 4 is given to a neural network model, then it should tell with a certain degree of accuracy that this resembles to a and this resembles to a digit 4. It should not tell that it is resembling 0, 1 or other than 4, that means. So what exactly you can see from this figure? So you can see there is a layer 1 representation, there is a layer 2 representation and layer 3. Now if I just ignore the input, then from the layer 3 you can hardly make out what it is. Then layer 2 also is difficult to make out what you are trying to give as input. Even in layer 1, only in one image to a certain extent we can think, like there are so many neurons or there are so many things are there as part of this layer 1 model, layer 1 of the model. Then it's also difficult even to layer from the layer 1 to say that okay this is 4, except probably this figure where I am hovering little bit it resembles to the digit 4. However, from the rest of the other images is difficult. However, what I just told you, so this is a layered representation. That means there is a transformation that has happened when when you are talking about such a situation. That means when you are talking about the digit classification, this is our example. So this network, that means the layered has basically transformed the digit image into representations. So now obviously these representations are different from the original image. However, all these representation that I am showing you in layer 1, layer 2, layer 3 basically help or basically aid to make the system decide that now this corresponds to a digit and return digit 4. So that's the beauty, and that's why the layered representation plays a role. So all these three layers are helping to decide that the digit input digit is 4. Similarly, it will do it for 3, it will do it for 0, it will do it for 8, like that. So deep network, why? Because now we are showing different layers. So there is a chance that you may not have just one layer or two layer, because typically when we talk about machine learning, then normally people tend to say at times as a shallow learning. So when we talk about deep learning, there are going to be multiple layers of representation. So essentially what now we are talking about a multi-stage information distillation, and that is what these layers, when we have taken this example as 4, you can see that increasingly meaningful representations are there, or for that matter there is an information distillation. Now when we say distilled water, that we have seen in chemistry, so that means now there is successive distillation that typically happens, and probably it purifies or it distills, the water is distilled. Similarly here you can see that multi-stage information distillation operation, that is what it is called in literature. So this information, that means this input, say digit 4 or for that matter any other object, goes through successive filters and comes out increasingly purified. So deep learning is a multi-stage way to learn data representation. So again emphasizing this point, data representation is a very important word that I have started using, and that's where this final definition we have arrived. So it's a multi-stage. Why? Because there are different stages and there are different stages. So that's why it is called multi-stage way to learn data representations. So now let's try to understand what is learning in DL. So let's now try to see this diagram. So where there is a input, that means input, it can be objects, it can be text, it can be images, it can be digits, whatever. Then you can see there are two layers are shown here, where we have written in bracket data transformation. So that's what I was telling, there's a transformation that will be there. So layered, this is again second layer, and then outcome, there is a prediction. And then you can see on the left hand side there is a weights as shown as an input to these layers. So input to target mapping is done via sequence of data transformations. When we say data transformation, that means it's a responsibility of now the layers that we have seen. Then data transformations are learned by exposure to examples, that means the input data. So what specifically a layer does to its inputs? That is stored in the weight. So that means this weight plays a very important role. That means this, say for example, this is layer 1 and this is layer 2. So what this layer 1 is supposed to do and what this layer 2 is supposed to do, so that will be governed by the input weights. So in a way, weights play a very important role, or weights governs the behavior of layer. So learning means finding a set of values for the weights of all layers. So that's where the precise definition of learning means that means you really need to find the weights which basically are able to help understand what is the input so that it goes nearer to the truth. So such that network will map correctly, or rather such that network will correctly map examples, that means inputs, to the appropriate targets. That is what I said, like it should go nearer or as closer to the truth or the true values. So what is the aim now? So obviously it's very easy now to say, so to find the right values for weights. However, now there are several numbers of weight, or several weights are there, they are called as parameters. So how do you now achieve that? So essentially now you are going to get predictions as part of your model, and then you compare that prediction with the true target or truth, that is y denoted as y, and your predictions are denoted by y dash, and then there is a loss function. So this loss function is going to tell the loss score, that means how close your predicted value, that is y dash, is to the truth, or how far it is from the truth. So that's where this particular thing comes. So to control the output, measure how far this output from the expected. So that's where I told you, that's where this loss function, or at times this is also depicted as, or also mentioned in literature as, cost function. So loss function or cost function, these are interchangeably used word. So loss function, it takes predictions and true target, then it's going to compute the score, and then the score tells how well the network has done for input data. Now what do you do with that? So now this score, you need to use it as a feedback signal, and then accordingly you need to adjust the weights, and that's where this particular module that comes into picture, and that is optimizer. So you adjust the weights so that loss score is lowered, or it keeps on reducing, and then optimizer basically implements an algorithm which is called as back propagation. So now the full picture is shown here. So you have the input, which essentially is fed to the layer. There are two layers in this diagram. You can have more layers. Then to each layer there are weights. Then these model, that means the layered structure, is going to give you the predictions y dash. Then you compare it with truth or the true targets. Then there is a loss function which is going to do that, and the job is to minimize this. That's where the minimize, that means the score should be minimal or it should be low score. Other, that means this score essentially now you need to feed it to the optimizer, and this optimizer is essentially going to propagate this information or the errors, and accordingly then the weights will get updated, and that's, this process will keep on happening, and such thing is essentially called as a training loop. So initially the weights, you can have it randomly assigned, then obviously because you have randomly assigned it, then it will be far off, so last score will be high. Then with every example you train, so with every example your model or your deep neural network model is going to process, weights will be adjusted in a correct direction. Now when you say correct direction, this is very important, and that's where the gradient descent algorithm plays a very important role. There is a separate video that has been provided about gradient descent as well as the mathematics about backpropagation algorithm as part of this tutorial series, which is deep learning tutorial series. So there are two aspects to it. One is the gradient descent, so it should happen in a correct direction, that is point number one, and the second point is you need to propagate the error, then only the weights can get updated. So that means now the correct direction is important, then only the loss score is going to decrease, and now that loss score decrease, that means the error has reduced, or the loss has reduced, or the score is lowered, that means that particular thing should get propagated, and that's where the optimizer or the back propagation algorithm comes into picture, and you have a separate mathematical treatment that has been given to handle these aspects like gradients as well as the back propagation algorithm. So what are the examples now? So examples are image classification. I have already mentioned to you, like you need to identify images of flowers, images of animals like pets, any pet animals like cat, dogs, say then you can have other pet like whatever you can have in your house. Then people basically have varied degrees of pets, so you can have that way. Then speech recognition, I already spoken about it. Then machine translation, obviously NLP type of thing. Then there are products like Google now, which is also part of your phones, in mobile phones, where there is recognition. Then Amazon Alexa is also another product. Then apart from that, very important product or very important place, there is application is there is improved advertisement targeting, and we can see that when you tend to use Google or when you tend to use YouTube, then it's going to recommend to you those videos or the products that you probably have browsed in Google or in YouTube. You have seen videos or whatever, I mean to say music or whatever you tried. So all those targeted advertisement is achieved through this approach of deep learning. Then ability to answer natural language questions. So essentially NLP type of thing also falls under this category. So now let's try to, having understood this deep learning, now let's try to understand what typically one needs to understand as part of this curriculum. So here one needs to understand what are the building blocks of neural blocks. So here one needs to understand a tensor, how do you represent data, then what is back propagation in short, and then obviously the back propagation along with gradient descent mathematical treatment is handled separately, but in general overall overview of back propagation also one needs to know at least. So bare minimum is required, and that is overview of back propagation one needs to know. So that is dealt separately in coming videos. Then keras, and that's what we tend to use to carry out hands-on activities. So where you need to understand the data set that is part of keras, then how do you apply keras to various case studies, then what do you mean by underfitting or fitting. Then one needs to understand the image processing or computer vision, where there is a convex or CNN neural network. So convex, it is basically mentioned as CNN. Then image features, how do you work on image features, then what do you mean by pre-trained convex. So all this will be is part of such tutorial series. Then how do you deal with text and sequences, so like how do you talk or how do you handle text data, then what is RNN, what is long short TM, that is LSTM, and then the last topic, which is a little advanced topic, which is about introduction to functional APIs, and a few more things about functional API are part of such topic. So that's essentially the various topics that one needs to understand as part of a deep learning course. So I hope you like this video, which was introduction about deep learning, and it also essentially tells you about the various topics that one needs to understand. Thank you. Hi, welcome to deep learning course. In the previous lecture, we have seen tensor and tensor operations. From now onwards, we are going to see keras and much more things so that we can make the things work. So my name is Sriran Korde, and let's now begin. So the topics that we will be covering will be keras, then ANN, that is artificial neural networks, then activation functions, and then the loss functions. Having done all these things, so we'll be ready to do a lot of things hands on. So let's get going with keras. So now when we talk about keras, the first question typically people will like to understand is about TensorFlow, because that happens to be the beginning point, or that happens to be the starting point when we talk about keras. So the first thing that we need to understand is TensorFlow. Now when we talk about TensorFlow, probably we know that in the last lecture we have seen the word tensor, and then we have done some operations on tensor. So now let's get into what is TensorFlow. So it's the most famous deep learning library, and essentially it is called as Google's TensorFlow. So obviously, having said this, it must be given by Google to all of us. So let's see first the practical uses of it. So Google product uses machine learning in its product. So Google product, essentially whatever the different products, so it's going to use machine learning in its product. And so where do they use? So essentially they use to improve the search engine, then whatever the searching that we do, so it uses there this techniques, then the translation, then the captioning of the image, or at times it does a lot of recommendations. So all these are the places where typically as part of machine learning Google has developed this TensorFlow library. So example is, so Google users can experience a faster and more refined search, and that I think we already have seen, and that's why that search engine happens to be the most popular. So if the user types a keyword at the search bar, so essentially Google is going to provide the recommendation about what could be the next word. So the example is, say for example, if I type say HUM, then it's going to show me so many options like human psychology books, or say the some names like Hum Saath Saath Hai, name of movie, or whatever, human body and stuff like that. Okay. So point just I'm just trying to make here is that this is where a lot of advanced things are going to come, and it's basically now used in sort of predicting or recommending what could be the next word. So that's the real example, and every day we have seen that, and that's where the Google's TensorFlow library is used for. So let's quickly understand the history. We are not going to spend too much time, but just to complete our discussion, we'll quickly spend some time on history. So why this thought process has come, or probably the starting point could be like Google has the world's most massive computer and data, and it's very obvious, like we know that, like most of us have Google email account, then we use Google Drives, and so many things, like I think there is no need for me to keep on telling all those. So essentially they have the world's most massive computer, and then they have the data. So TensorFlow essentially was built to scale, because if that library would have been just for say it's working only for say limited amount of data, then probably it would not have been useful. So the first approach, or the basic thought process, was like it should be built to scale. Okay, that's very important, and they had the data in computer. So computer doesn't mean that a big computer, it can be a combination of several small computers. Okay. So TensorFlow essentially it's a library developed by Google Brain team to accelerate machine learning and deep neural network research. So you can see that now we are able to link those thought process. So it's a library developed by Google's Brain team to accelerate ML and the deep neural network research. So it's built to run on multiple CPUs or GPU, and that's where I made that a few minutes back. I made a comment that it has the world's most massive computer. Doesn't mean a big computer. It means like you have the different computing units. They are all well connected and stuff like that. So essentially, you require a solution which will be ready to build, which will be ready to run on multiple CPUs or GPUs, and even on mobile operating systems. And then apart from that, it has several wrappers in Python, C++ or Java. So that also is one of the important reason or primary reason that it's very popular and people use it. So Google used deep learning neural networks to improve services of. So initially I had told you about the ML stuff. Now we can see that it is going to use some techniques or this library for deep learning neural networks to improve services of Gmail, then the photo search engine. So these are some of the examples. So for that, Google built a framework called as a TensorFlow, and it allowed researchers and developers like us, so essentially who are basically trying to do our own R&D or trying to learn and stuff like that. So it allowed researchers and developers to work together on an AI model. So that's a very interesting thought process. So once developed and scaled, it allows lots of people to use it. So it was essentially made public in late say 2015, and then the stable version was released in around 2017, and then essentially it comes under Apache open source license. Okay, so that's basically the brief history of TensorFlow. Now the question typically will come to your mind. I started with the topic that I'm going to explain you Keras, and then why did I basically started with TensorFlow. So obviously as we proceed forward, it will become evident. So let's spend some little more time on TensorFlow. So from where this name came actually. So it's called TensorFlow because it takes input as multidimensional array, also known as tensor. So in our previous videos, we have seen what is a tensor. We have done what are the different operations on tensor. So I think now it's very clear. So essentially it's going to take multi-dimensional array as an input. Okay, and that's where the name has come from. Apart from that, so what does it do after taking those multi-dimensional array or tensor? So it's going to construct a sort of a flowchart of operation, and that is typically called as a graph. So whatever the operation that you want to perform on that input. So input goes at one end and then it flows through this and system of multiple operations and comes out the other end as an output. So that is where this, the name has come from. So what does it mean basically? So let me just highlight this. So tensor flow, that is, the tensor goes in it, flows through the list of operations and then comes out the other side, and that's where this word tensor flow has come. That means you have this tensor which happens to be the input, which is essentially multi-dimensional array. It flows through and that means it's basically flowing through the list of operations, and I have told you it's a flow chart of operations, so called as a graph. So that I have already said above. So the tensor goes in and it flows through a list of operations and then it comes out the other side. So let's quickly take a look at both these things, tensor and TensorFlow. So in TensorFlow, all the computations involve tensor. I'm just trying to recap what we have seen earlier as a tensor. Then a tensor is a vector or matrix of n dimension that represents all types of data. Then all values in a tensor hold identical data type with a known shape, and at times partially known shape, because it's many times there are situations where you may not be interested in the other dimension. One dimension is good enough. Okay, so point here is all values in a tensor hold identical data type, and the shape at times known or partially known. And tensor can be originated from input data or the result of a computation. It's very common sense that intermediate stages also, or the output also, you are going to get the tensor. So TensorFlow now. So all the operations are conducted inside a graph. So I'm just trying to summarize. So I have said this earlier. Then the graph is what? It's a set of computation that take place successively. Then the technically that operation is called as opnode. Okay, operation node or opnode. And all these such opnodes are connected to each other, because that's when then you are going to perform, or those operations are conducted inside a graph. Okay, so graph outlines the ops or the operations and the connections between the nodes. So essentially that's what the graph is basically. So the graph outlines the operations, whatever the operation, and the connections between the nodes. Then the edges of the nodes is tensor, obviously, because that's what we said, tensor in. So the edge of the node nodes is the tensor, that is a way to populate the operation with the data. Now we'll go to the keras. Now the question probably would have been in your mind is, why did I start with TensorFlow? So now let's get and let's go into the keras now. So keras is what? So essentially it's an open source neural network library written in Python, and that runs on top of something. Okay. So it runs on top of multiple such things. So one such library is basically Theano, and it's basically a University of Montreal, Canada, Quebec, Canada, basically have developed. The second one is TensorFlow, and that's why I started talking about TensorFlow. Now probably it is very clear that we are going to use keras, but however we need to know a little bit about TensorFlow without going into too much of details. Then the third one that keras is going to run is CNTK, which is basically a cognitive toolkit by Microsoft. So these are the three I will say backend on which keras can run. Okay, so keras uses library called the backend to do the low level computation. That means the lower level computations can be performed by Theano or TensorFlow or CNTK, and then keras is going to make use of those operations. So that means sort of keras is subcontracting the work which needs to be done at low level to the backend layer. So keras is what now? Obviously it's that's very clear now. So keras is a high level API wrapper. It's capable of running on top of TensorFlow, CNTK or Theano. So keras API, so obviously when we say that it's a high level application programming and interface or API, so it's going to handle now it's going to do some job, or those APIs are going to do some job, and that's where I'm going to rely on keras rather than directly using TensorFlow. Okay. So it is helping me to do making of models. That means I can make neural network model, and it gives me like a function like an API. That means as if I'm just trying to call a function the way in which we probably call function in say Python or in C language. So we just use it sort of a library. Suppose if I want to do some operation, so for example if I want to do say string operations, then I can make use of some string.h library and can make use of those functions, say in, for example in C. So in the similar lines here, I can make models, and that typically is called a neural network model. Then I can define layers, okay, because I have already introduced you as part of the introduction that the layers is very important when we talk about deep learning. So I can also define layers or set up multiple input output models. So essentially that is where we have seen that as part of introduction, and Keras helps me to achieve that. Then it also compiles the model, because now I am going to define a model. So obviously the way in which we write a program, say for example when we write a C or a C++ program, then it has to be compiled. So similar thought process, or on the similar lines, Keras needs to compile the model with functions. Okay, so we'll see these functions later because that's part of our next presentation. So we'll see that. But Keras is going to compile the model with functions like loss functions or we'll see that. Okay, and the training process. So compilation is again important issue, important point. Then Keras doesn't graph. That means Keras does not graph is computational graph and is handled by the backend agent. That's why I started with talking about TensorFlow. So Keras is not going to do the computational job. It's basically the responsibility of the backend layer. In our case, it's going to be TensorFlow. So that's what basically completes the presentation. So in this presentation we have seen about TensorFlow and then the Keras, and how Keras relies on TensorFlow, and what is the tensor, and what is the TensorFlow, and what is the Keras. So probably now we are a little bit aware of those these terminologies. So in the next lecture we will be talking about artificial neural networks. So thanks for watching this video. Thank you. Hello friends, myself Shriran Kode. So as part of this video, we will understand layers. Why? Because one needs to understand artificial neural network and where layers fits into. So now let's try to get into the detail. So the overall approach that we are using for understanding artificial neural network, or for that matter even the deep learning, basically is like you have the input X, and then you get your predictions Y dash, and then you essentially measure it with the truth or the true target, and then there is a loss function. So that means when we talk about training a neural network, so it revolves around few things like layers, which are combined into neural network model, and layers are responsible for doing data transformation, then the input data and the corresponding targets. Then there is a loss function which defines the feedback used for learning, because you have a optimizer which determines how learning proceeds, and that's where this backpropagation algorithm also fits into it. That means now you have the score as a feedback signal, then accordingly the weights are adjusted so that the score is lowered, the loss score is lowered, and then there is an optimizer which is basically implementing the backpropagation algorithm. So having laid this basis or the overall structure, so now let's get into the artificial neural network, where we will try to understand it with respect to how a brain performs, or how brain overall works, and it's at very top level we are going to understand. So the brain is capable of performing quite complex computations, and that's where the inspirations for artificial neural network lies into. And then when we talk about human brain, so it is composed of number of neurons. So essentially we are talking about biological neurons which have dendrites and axons. So we can see in this diagram there is an axon. So axon is like a connector, and then dendrite is like where you are basically going to collect. So neuron collects inputs from other neurons using dendrites, and a particular neuron is basically going to sum all the inputs, and if the resulting value is greater than a threshold, then it's going to fire. Now this overall structure we need to keep it in mind, and then obviously if the neuron has fired, then the fired signal is then sent to the other connected neurons through the axon, because axon acts as a connector. So having understood this basic model, now we are going to take it forward. So the single artificial neuron is a simple tree structure which has input nodes and a single output node, and which is connected to each input node. So that's in general the structure. So we can show this diagrammatically, like you have this x1, x2, x3, then there is w1, w2, w3. So that's where essentially you have the weights, and then you can see there is a summer or a summing activity, and there is something called as activation function, and then you have the output. So essentially on the left hand side there is the input, or there are inputs, and then you have the output. So here you can see this x essentially is summation of all the inputs multiplied by the weights, and then there is a bias. Now this bias itself happens to be one of the research area. However, broadly speaking, this is more like a level that you, because your inputs can be negative, your inputs can be positive, x can be positive, negative, that means the values can be positive and negative. So how you want to process, that means what bias you need to provide, so that particular thing is a bias, or that particular level essentially is comes under bias. So now let's see the output. Now essentially this output is multiplication, or essentially it's like it's equal to activation, and to this activation we are feeding the x. Now what is x? X is a summation of all the inputs. So that means output, this function f which is shown in this diagram and where I am hovering the cursor, so this particular function is basically the activation function. So essentially output is fx, or function of x. So a neuron now is connected with other neurons, and that particular structure is typically referred in literature as perceptron. So a neuron, that means a single neuron, is connected with an other neuron, so that structure is a perceptron. So that means now it's going to receive n inputs, and those n inputs can be x1, x2 till xn, and then the inputs x1 to xn, and the weights w1 to wn are essentially the real numbers, and it can be positive and negative, and that's what I was trying to tell you, because your input also is a real number, your weights also can be positive, negative. So essentially you basically can have both, either positive or negative, and that's where the bias is required. So essentially now the perceptron is what? So essentially it consists of weights, then there is a summing operation, or a summation processor it is referred as, and then there is a activation function. So all the inputs are individually weighted, that's what the diagram was showing, then they are added together and passed into the activation function. Now there are various types of activation function which we are going to study later. However, for this particular video, or for this particular lecture, we will understand one of the simple activation functions, and which we are going to also use as part of this video. So step function happens to be one such activation function. So step function is like a rectangular wave, like we can think of like, suppose if I want to just draw it, then I can just draw it like this is a step function. You can see this is like a step function. So a step function will output 1 if the input is higher than a threshold, otherwise the output will be 0. So it's like your step that you have in a staircase. So this is essentially a activation function. The key point here is that if it crosses a threshold, then it's going to output 1. That means suppose if I depict this particular thing as 1, that means the top level of the square wave is happens to be the 1, then the bottom line will be the 0. Okay, so that is where this particular thing will be 1. So a step function will output a 1 if the input is higher than a certain threshold. So there are other activation functions like sigmoid and ReLU, which we will study in further videos. So let's now see how do I make use of such a step function which is a 0 or 1. So let us say you have input x1, which is one input, and let us say the input value is 0.6, and another input say input 2 or x2, his value is 1.0. So here there is a weight for each of the input, as I mentioned to you in the previous slide. So suppose that weight 1 is 0.5 for x1, and weight 2 is 0.8. So now we are going to do the summation, and now this is very important. Let us say that I am going to give threshold. Now this is my decision. That means I will decide when it should fire, or when this function comes into picture, or when it doesn't come into picture. That means when should it fire. So here you can have x1 w1 plus x2 w2 is equal to 0.6 into 0.5 plus 1 into zero point 0.8. So essentially this will become 1.1. So now you can see this 1.1 is bigger or is higher than the threshold, and thus the neuron fire. So this is very important. So neuron has fired. So now we have understood how typically the neuron will fire depending on that summation, and we have seen this activation function, which is a step function. Now comes the understanding of the modifying of the weights. So the input vector from a training set are presented to the perceptron. So let me just switch back the pointer option to the laser. So input vectors from a training set are presented to the perceptron one after the other, and the weights are modified according to the equation. Now comes the understanding about how the weights can be modified. So weights are modified by this equation, that is for any of ith weight. Basically ith weight is equal to the previous value of ith weight plus something called as learning rate, which is denoted by either alpha or a. Some literature denotes a, some literature may denote it alpha, but it's the same thing. So a multiplied by t minus a into p of I. So now this p of I is basically the input. So now this actual equation is wi plus a star a into g dash of all the inputs, sum of all the inputs, and then multiplied by t minus a into p of I. Now this g dash is the differentiation or a derivative of the activation function. Now we will study this little later, but that's the actual equation. However, if I want to calculate the derivative of a step function, then essentially it's a impulse. That means it shoots up to infinity. So that's why we ignore that as part of usage of a step function as an activation function. So that's why this simplified equation is shown here, and I am hovering the cursor or this pointer, where wi is wi plus a into t minus a into p of I, and this particular derivative for step function is ignored. Why? It is problematic to deal with the derivative of step function. So what is w? As we know, it's a weight vector, then p is the input vector, and then t is the truth or the correct output that perceptron should have known. So t basically corresponds to truth, and a is actually the actual output given by the perceptron, or essentially it's a predicted one. So this is the equation which typically plays a role where we will be able to modify, or the weights are modified. Now this equation is a general equation. Why? Because even the learning rate is part of here, part of this equation. So learning rate also plays a role when we talk about gradient descent, and in the videos related to gradient descent, such topic is also dead. So let's continue now. So an input vector now p is given to the perceptron. So it is going to output the correct value if p is already in the training set. Why? Because we are going to give some inputs as for training. That means like the example where we have seen, okay, a person is learning to identify the objects. So we show the different objects like car, dog, cat, and all that. So that means as part of training we need to show some samples, and then you basically test how it is performing on a new sample. So suppose if the input vector which was used for training, so it is a part of the input, then it's going to output the correct value. If p is not in the training set, then the network is going to respond with an output which will be similar to the other training vectors close to p, and that's where the prediction comes into picture. And that's why you have to have a loss function. Why? Because now for a new training or new data which is different from the training set, there is a chance that your output will not match the correct one or the truth one, and that's why you have to use the loss function. So the perceptron is adding all the inputs and separating them into the two categories, and that's what we have seen when we basically use the step function. That means it's either going to fire or it's not going to fire. So that means those that cause it to fire and those that don't. So not every sets of input can be divided by a line. Why? Because now this is a very clearly laid out activation function. That means either it will be fired or it will not be fired. Now there are cases where there is an input which you cannot take such a decision. That means now whether it is firing or whether, that means whether it is 1 or whether it is 0. And if it is, if we are able to do the division of the input, that means of the, say for example the training set, then we call such a data as a linearly separable data. However, not every data will be like linearly separable data, that means by separation by a line. So if the vectors are not linearly separable, then in that case what will happen, it's not going to reach a point where all vectors can be classified properly, that means the learning may not be complete. So then it is typically referred, such a data can be referred as non-linearly separable. Why? Because we have chosen activation function according to basically the step function. Okay, so in that case you need to work on the activation function, and that's why we will learn more about activation functions in further videos. So now let's try to understand a multi-layer neural network having understood a very simple structure. Now you can see in this diagram there is an input where there is a pointer. You can see I am showing you this is the input, and then there is a hidden layer. Now these hidden layers can be multiple also, and then there is a output layer. Now you can see this input layer is every output, that means this input layer is connected to all the nodes of the hidden layer. So typically this hidden layer will be something dense, it is also called as dense layer or a fully connected layer. Okay, so each input from the input layer is fed to each node in the hidden layer, and from there to each node on the output layer. So there can be any number of nodes per layer, and there are multiple hidden layers. That's what I have mentioned to you. And you can have multiple hidden layers to pass through before ultimately reaching the output layer. So to train such a network, a learning algorithm is now needed, which should be able to tune what? So it should be able to tune the weights between the output layer and the hidden layer. Now that is okay, because I have told you the equation, like you have the equation and you can modify the weights, and then you can obviously differentiate the activation function. Now taking a derivative or differentiating itself is a big topic, and I will touch upon it in few slides later. But point here is like the weights between the output layer and the hidden layer. So to train this network, a learning algorithm is needed which should be able to tune the weights between the output layer and the hidden layer. Okay, and also the weights between the hidden layer and the input layer. Now that is where the important issue, or that's where the back propagation plays a very important role. Why? Because now hidden layer, because you have the truth here and you know the actual output, so you can always find out the loss. However, how are you going to take it back? That means how are you going to update that effect should happen between hidden layer and the input layer. That's why you see I have shown it in the red color. So to tune the weights between hidden layer and the input layer, the error at the hidden layer should be known. Okay, however, but we know the error only at the output layer, and that's what I was trying to mention to you earlier. That means the correct output from the training sample and the output predicted by the network. So that's where this back propagation algorithms comes into picture, and which is going to take the errors at the output layer and it's going to proportionally propagate them backwards to the hidden layer. Now this itself is a very big topic. Why? Because if you have a very deep network, then in that case propagating them backward itself is a question mark. There is a chance that whatever you are trying to propagate itself get diluted and it hardly reaches the input layer. So that's why this itself is a research area, and people work on these algorithms or such schemes and the structures which are part of deep learning, or for that matter the neural network. So let's now try to understand brief about the back propagation algorithm. So now you see there is a input which is shown as x1, x2, x3. I am taking a very simple structure here, and there is a output s. There is only one neuron at the output, and then there is a hidden layer 1, and then there is a hidden layer 2. So here you can see this is a1, a2, a3. These are all the activation functions. These are rather the activations used, and then once again there is activation used in the hidden layer, or that means hidden layer 1 and hidden layer 2. So here xi is essentially is same as ai. Why? Because it's the first set of activation. So a is essentially the input value. That means just we are passing it. Okay, so that's what an I is basically 1, 2, 3, 4 here. Then the hidden layer output 1, that means it's a layer 2. So please understand it. So this input layer was a layer 1. So this hidden layer 1 essentially is a layer 2. So here you can see this Z2 2, now here subscript is removed purposefully, and I will tell you the reason later. So z of 2 essentially is weight into x, that means whatever the x vector plus the bias. Okay, now let's not worry too much about bias. I have told you earlier what is bias. So then the a and then the 2, that means at this particular layer 2, a2 is equal to f of, the f is essentially the activation function, and then it's a f of z, z2 essentially. Okay, so then similarly the layer 2, hidden layer 2 output, that means it's a layer 3. So you can have z3 is equal to weight into a2 plus bias. So that means a3 essentially is a activation function f, which is denoted by f, and z of 3, z3. Okay, so here you can see this w2 is not a square or a cube, but it's essentially at that particular level. So w2 and w3 are the weights in the layer 2 and layer 3, while b2 and b3 are the biases. Now here you see there is a, we are going to make use of a matrix representation, and that's why this subscript is missing, or subscript is purposefully avoided. Why? Because we are going to use the matrix representation. Essentially it's going to be a vector, or for that matter it's a matrix. So that means for layer 2, W1 is a weight matrix of shape n by m. So where n is the number of output neurons, that means neuron in the next layer, and m is the number of input neurons in the previous layer. So here you can see n is 2 and m is 4. So let me just take you back. So here you can see this previous there are 4, and in the hidden layer there are only 2 neurons, which are shown in green here. So that's why here you have n is equal to 2 and m is equal to 4. So now you are going to have this weight matrix as W11, W12, then W13, and which is essentially of the shape n by m. So you can see this n by m, that means 2 rows and 4 columns. Then x is the input vector, as I told you, so which is depicted, that means there are 4 input neurons which I showed you in the previous slide. So x is essentially a vector which is composed of x1, x2, x3 and x4, where m is equal to 4. So to summarize, now here layer 2 there is a weight matrix, and then there is a input vector. Now when I say layer 2, that means it's the output of hidden layer 1. That should be clear. So that means now the overall equation will be that will be Z2, that means output of hidden layer 1, that means output of layer 2 will be a matrix, weight matrix, which is essentially weight into x, that means this is what Wx, summation of weight into x. So this has been shown here, plus the bias. Bias is also, there are 2 biases, B1 and B2. So this is what you can see in the diagram now. So this is the input, and then this is the hidden layer output of hidden layer 1, which is essentially layer 2, and that's why you see layer 2 is mentioned here, which is essentially hidden layer 1. So Z of 2 or Z2 essentially is Z1 and Z2. So which is again a matrix, or a column matrix we can say. Then the output layer. So this output layer, so you continue like this. So output layer is now basically is a predicted value. So which is a single neuron, as was shown to you in the previous slide. So this is that single neuron, which is S. So this is what now we are going to make use of S. So this S is equal to now W of 3, obviously it's the third layer, into a activation function, that means at the third layer. So now you need to have a loss function, or which is also depicted in literature as cost function. So now you evaluate between the S, that means this is the predicted value, S is the predicted value, and Y is the truth. So how do you do that? So for that there are different ways. So people use MAC, and in the when we talk about gradients and all that, you will see how we make use of this MAC and all that. So in that video you will see this, but MAC essentially stands for mean square error, and there can be other example like cross entropy. So what is cross entropy will be clear in our further videos. So let's not worry too much about this. Right now we will think of loss function as some function, say for example mean square error, which is just the square of the values. Okay, so and then you take the square of that, and then you can have the root and all that. So there are few calculations. So let's not worry too much about it for the time being. So C is essentially, or the loss function L, which is the loss score, which I was trying to tell you, essentially the function of S and Y. So that's where this backpropagation algorithm comes into picture. So based on the value of C, adjustments of parameter, that means of the weight, is done. so that you get closer to the truth. So in the literature, what it is written as, it's repeatedly, this algorithm repeatedly adjusts the weights of the connection in the network so as to minimize the measure of difference between the actual value and the truth, that means desired output vector. So this repeatedly, this backpropagation algorithm is going to compute the cost, or rather the cost is computed, and then accordingly these values are basically repeatedly adjusted. Okay, now comes a very important aspect of backpropagation algorithm. So this backpropagation algorithm, as mentioned to you, it minimizes the cost function or the loss function, and that's why I have told you about loss function earlier, and we will study loss function in detail in further video. So this backpropagation algorithm minimizes the cost function by adjusting the weights and biases. Then the level of adjustment is determined by the gradient. Gradient means you are going to take differentiation or a derivative. So you are essentially going to take derivative of the cost function. So when I was trying to tell you the overall algorithm, that's where I have mentioned to you summation of x plus uh, that you have to have the derivative, that means gradient of the summation, and then multiplied by t minus a, and all that I have told you as that equation. So this gradient of the, here now the here the cost function essentially is a loss function. So you have to take the gradient of the loss function with respect to the these parameters. Okay, so that means now you have to have the partial differentiation. So how do you carry out this? So for that one needs to carry out partial differentiation, and then we rely on the chain rule. Why? Because now that particular differentiation that you carry out, basically we are going to make use of this chain rule, which is depicted as g of fx dash is essentially g dash fx into f dash x. So here g dot of f denotes the function composition, which is of x, then fx, and then g of fx. So that's what I am trying to tell. So this chain rule actually is playing an important role when we are trying to propagate the things backward, and then only the weights can be adjusted so that it reaches the input layer. Okay, so that's where this backpropagation algorithm plays a very important role with respect to uh, uh, chaining, or with respect to carrying this. So there is a separate mathematics behind it, and which typically gets covered as part of very other video, where you have the only mathematically things which are dealt as part of backpropagation algorithm, and the gradients, that means how do you carry out the derivations, and then how do you talk about doing the propagation back. Okay, so that's where the mathematics plays. So right now we are not going into those aspects. So the overall structure is like you need to carry out the gradient, that means you need to carry out the differentiation, partial differentiation is used, and then we are going to apply the chain rule. So let's now summarize without going into mathematics, too much of mathematics. So summary of backpropagation algorithm: initial values of W and biases are randomly chosen. Then a learning rate essentially determines the gradient's influence, and in the video related to the gradient, we definitely speak about the learning rate. Then derivative of matrix, rather derivative of cost function in W matrix can be calculated using the partial derivatives. So I just told you partial derivatives of C in the individual weights or biases. Then termination condition is met when the cost function is minimized. Now this cost function minimization itself is a important aspect. So now let's try to summarize the ANN. So training sample is presented to the neural network, initialized with the random weights. Then you compute the output received by calculating activations of each layer, and thus calculate the error. Having calculated the error, readjust the weights such that error decreases. Then continue the process of all training samples several times until the weights are not changing too much. That means you have reached a place where weights are more or less stable. That's where you say that your network has learnt, or it can tackle new data. That means training is more or less complete. So that's essentially about this video, where we talked about neural network. So we essentially understood the layers, and then we talked about neural network, artificial neural network, and then we spent significant time about the backpropagation algorithm and some aspects related to the mathematics of it. I hope you like this video. Thank you. Hello friends, myself Shrirang. In this video we will concentrate on two things and which are pretty important, that is optimizer and another is activation functions. So again this is part of deep learning that one needs to understand. So we already have seen keras, we already have seen ANN. Now we will go into these two things, that is optimizer and activation functions. So let's quickly understand about optimizer. So when we have seen deep learning, so this is the reference figure that we have already used, where we have input, then there are predictions, and then which gets compared with truth or the true target, and then there is a loss function, and then the loss score gets sent to optimizer module, and then accordingly the weights gets updated, and that's the way typically the data transformation occurs at the layer level. Now that is the overall approach that we are already aware. So here we already know that the score is used as a feedback signal, and then you basically adjust the weights, and then there is a backpropagation algorithm which we have seen in a separate video about this particular algorithm, that means as an overview, as well as we have spoken about the derivatives and how do we basically carry out the chaining of derivatives. Now having laid out this background, now we need to understand the optimizer more. So when we talk about optimizer, now how typically the optimization is going to happen, because as the name suggests, optimizer means essentially the things should be optimized in such a way that the loss basically gets minimized and the way in which we are going to do that is like the weights are getting updated or modified, and the loss gets reduced. Now to achieve that, essentially we need to have a algorithm, and that algorithm is typically called as gradient descent. So this particular method is used for analytically finding the combination of weights that yields the smallest possible loss function, and that is what overall goal is also. Now how that is possible, because I already have told you, like we need to carry out a derivative of a function. So that means that function should be differentiable. It's theoretically possible to find the minimum. That means when you have a function which is differentiable, then only you can find a minimum, otherwise this is ruled out. So functions minimum, that means why you do that? So essentially when you find the minimum point where the derivative is 0, so that is what the functions minimum is, a point where derivative is 0. Now this we know as part of learning mathematics in our say early college days. So you need to find all the points where a derivative of a function goes to 0, and accordingly then you need to check for which of these points which has a lowest value. Why? Because the derivative can go to 0 at multiple points. However, we are interested in the point which is having the lowest value. That means now we have started thinking of a situation where you have a sort of a global minimum value, and then there is something local minimum value. Now here essentially we are talking about something called as momentum, and that is where we are interested in. Why? Because how quickly or what is the momentum what is the momentum actually which is there, which reaches or which takes me towards that minimum value, and we are obviously interested in lowest value, and that should be at the global level and not just at the local level, and that's where this optimizer atom plays a role. Now this optimizer atom is typically used, and we are going to use that later. So here this is similar to the gradient descent technique. So ADAM is an optimization algorithm and it is similar to gradient descent, and gradient descent algorithm working is given as part of separate video. So that's why we are not going into too much of detail right now. So Adam essentially has come up with his own way of doing the things. However, it is a modification or improvement, I will say, over the gradient descent. So here it will update network weights, and it is done on a iterative based. Okay, so it is like an iterative way of updating the network weight based on the training data. So now how this is done and what is the difference with respect to the routine gradient descent is, here a learning rate, because when we talk about the gradient descent and there is a learning rate, that means now we need to also understand the momentum. We need to see how basically, or how quickly or how slowly, that means how fast or how slow, or we are reaching to the minimum value. So here, as part of this Adam approach, learning rate is maintained for each network weight. That means each parameter we are going to have a separate network weight, and this particular approach basically helps to separately adapt as the learning unfolds. So that's essentially a quick overview about the optimizer Adam. So essentially it's similar to the gradient descent, and you are given a separate video on gradient descent. That's why we are not going into the details. So just telling you the difference. So here the main thing or important thing with respect to Adam optimizer is a learning rate is maintained, and which basically helps a better adaptation as the learning unfolds. And that means when we say learning unfolds, that means the iterative based approach basically unfolds. So having understood this thing, so now there is something called as optimizer, and that optimizer is an RMS prop optimizer. Now this is another optimizer. So here RMS prop is again, it's a gradient based optimization technique which is used in training neural data, and it balances the step size. That means now here the focus is more on momentum. So what does it do? So it decreases the step for large gradient to avoid exploding. That means to going away from the minimum, or and apart from that increasing the step. That means it is going to do the balancing. So it is increasing the step for small gradients to avoid vanishing. That means either it should not become too large, or it should not just it should not just vanish, or it should not become like it's not available sort of. Vanish means it's not available. So it is going to balance the step size, and that means it's essentially going to balance the momentum. So that means now the learning rate changes over time, so using a moving average of squared gradients to normalize the gradient. So now here what is happening when it comes to the uh, RMS prop optimizer? Again, it's a gradient based technique, so that is obviously now clear to us. Then the main thing here is that it's going to balance the step size and the learning rate. Then accordingly the learning rate changes over the time, and it typically makes use of a moving average. Now when we talk about moving average, so that means we are talking of a window where we are basically moving that window, and here we are talking about the squared gradient. That means the square of the gradient to normalize the gradient, so that you may have negative or you may have positive. So to avoid that, typically we work with squares. So here the learning rate basically changes over the time. So these are basically the two things. That means first is the Adam optimizer, and another is a RMS prop optimizer, and there are subtle differences. However, both are based on gradient descent approach. Now having understood this optimizer function, now we need to, or optimizer functionality I will say, so we now need to get into the activation functions. So this is the diagram that we are aware. Like when we are computing the x, then essentially it's a sum of all the inputs, and it's a weighted sum. Then the output is essentially the fx, that means activation is a function. So output is equal to fx. So that is what we know when it comes to the so output is f of x. So that is what, so activation is a function. Okay, and we have seen one such activation function earlier, which was a step function, and I have told you like we need to carry out derivative when we are talking about modification of the weights. So the other activation functions are like linear function. So this linear function is, as we now know from the basic mathematics, the equation of a linear function is essentially it's a straight line, like y is equal to mx or y is equal to ax. So here now if there are multiple layers in a neural network model, then if all are going to make use of this linear function, then that means the final activation function of the last layer is nothing but just a linear function of the input of the first layer. So what is the range now? Because now you have a situation where y is equal to say a1 plus a2 plus a3 like that, or m1 plus m2 plus m3, because we are now talking about a straight line. So here now you have a range, and that output will be from minus infinity to plus infinity when we talk about a linear function. Then comes a very important function which is an activation function, and that is a sigmoid function. So sigmoid looks like S shape, and that's why it is typically referred as sigmoid. And as we can see from this diagram, the values are from 0 to 1. That means now you have a S-shaped curve where the values below or less than 0 essentially will come under the 0.5 or less than 0.5 rather, and the values which are 0 onwards they basically will fall above 0.5, and that means it's going to map to the shape or a sigmoid function. So it is plotted as a S-shaped graph. Then what is the equation of such a graph? So the equation is 1 upon 1 plus e to the power of minus of x. So now you can see that I am having 1, and then 1 gets divided by 1 plus something. That means now inherently I am going to get a value which will be lesser than 1. Why? Because I am dividing number 1 by 1 plus something. So obviously I am going to uh, uh, have a value which will fit between 0 and 1. So the value range is 0 and 1. So this is used, and we will use this as required. This is used in the output layer. That means now you have a multi-layered neural network, and this particular activation function is used as part of binary classification. Now the binary classification examples can be like when you want to classify say images of say cat and dogs. That means you have multiple images of cats and multiple images of dogs, and you want to now new image is given either of dog or cat. Then you would like to classify whether it is a cat or dog, or even for that matter you can use this sigmoid function when you want to uh, assess whether an email is a spam or whether it is not a spam. That means like two values, whether yes, no, or spam or not spam, or cat or dog. That means between two values when you want to take a decision, then the sigmoid function plays a very important role, and it is used as part of the layer. So so here obviously as mentioned the result is either 0 or 1, as value for sigmoid lies between 0 and 1. So result can be predicted easily to be 1, that means if the value is greater than 0.5, and 0 otherwise. So now you can see here that sort of that cutoff I will say is like a 0.5. That means the value above 0.5 will be 1 and below 0.5 will be 0. Then another very popular function which is a ReLU function. So ReLU or ReLU, either way you can pronounce it. So this looks like a typical semiconductor diode characteristics. Only thing is that here we are showing it from 0. The semiconductor diode, the people who have studied it as part of electronics, it will have this curve begins at around say 0.6, around roughly 0.6 to 0.7, and then there will be this straight line. So I am hovering this pointer. So same way. So that's why it is called as rectified linear unit. So you can see that this word has comes from diode rectification graph. So rectification linear unit. So ReLU stands for rectification linear unit. It is most widely used activation function. Then this is mainly implemented in hidden layers of neural network. Okay, so because now you will have multiple hidden layers, there is a chance depending on how you define your model. So typically ReLU will be used. So the equation of ReLU is like maximum of 0 comma x. So you can see that minimum value will be 0 and max can be any of the value of x. So it gives an output x if x is positive, and otherwise it is 0. So mathematically is depicted as rectangular bracket for 0, that means it is capped, and then on the right hand side it can be x, that means it can go till theoretically it can go till infinity. So it is non-linear, can easily backpropagate errors, and have multiple layers of neurons being activated by the ReLU function. So that's the advantage. So it can easily backpropagate the errors, and you can have multiple layers of neurons getting or being activated by the ReLU function. Then it is the biggest advantage of ReLU is it's less computationally expensive. Why? Because you can quickly take like 0 or max, that means maximum of 0 to x can be quickly found out over sigmoid. Why? Because sigmoid is 1 plus 1 upon 1 plus e to the power of minus of x. So that computation is a little complicated or expensive I will say. Compared to that, ReLU is a very simple operation or mathematical operation. So when you basically are going to involve ReLU as an activation function, then only few neurons are involved, and that's why it is less computationally intensive. So few neurons are activated, making the network sparse, that means and making it efficient for and easy for computation. So that's why people typically call it as ReLU learns much faster than sigmoid function. Then apart from that, you have another activation function which is called as softmax function. So this softmax function is also a type of sigmoid function. So you can see here it's not like an S shape. However, after certain value, that means 0, 5, 10, like that, you can see here. So roughly say some number, this is not 0, 10, I am just showing you for the sake of showing you, and then there is a curve which goes up. Okay, so this is similar to sigmoid. So this looks like an S but is not completely S. Okay, so it is useful for handling classification problems. So it is non-linear, then it is usually used when trying to handle multiple classes. So let me just give you some simple example. When you say multiple classes, let's say that you have you want to categorize say dry fruits. So now the dry fruits are like cashews, then you can have kishmish, and then you or raisins, and then you have the say almonds. Okay, so these are the three categories. So like raisins or kishmish, some people call it as kishmish or raisins, then cashew and say almond. So these are the three different categories. Now what will happen is like you have trained the model that okay, this if this type of structure is then it's a cashew. If this is a structure, then it is an almond, and then if this is a structure or color, then it is a raisin. So when I give the new data of say raisin, or if I give the new data of cashew or almond, then you need to find out how near it is to the cashew, whatever you are trained, or it is near to say raisin or to almond. Then in that case, you need to categorize like in a multiple classes. So that's where this softmax function comes into picture. Why? Because it squeezes your output for each class. Now here the class is like there are three classes here, like one is raisin, another is almond, and another is cashew. So it is for each of the output. Why? Because now when you give new raisin picture or when you give new almond picture, then obviously it's going to tell you a number which will be very high, or which will be closer to the truth. Okay, it cannot give the ideal answer. Okay, it will be near. So that means you need to classify between 0 and 1. That means for each it is going to classify say between 0 and 1, and you basically will make use of softmax in that scenario. So essentially softmax function squeezes the output for each class between 0 and 1, and would also divide by the sum of the output. So that's a advantage. Then softmax function is used in the output layer of the classifier, where we are actually trying to attain the probabilities to define the class of each input, and that's what the example I just gave you to identify raisin, cashew and almond. That means identification of dry fruits in these three classes. So you essentially are going to work on probabilities, and higher the that means for a class where there is a higher probability, that is where that input data is matching. Then apart from that, you can use it in other cases also, like you have images of cars, then you can have images of say your clothes, like you can have t-shirts, pullover and all that. So you would like to categorize that. So again, and that's where this activation function can be used. So what it is doing, so it is distributing the set of numbers into probabilities of available class. So that's the way typically in literature it will be told, and I was trying to explain to you the same thing. So what is the choice now? Because we have explained or we have seen multiple activation functions, okay, like step, then linear, then sigmoid, and then the softmax. So how do you go about choosing the activation function? So the rule of thumb is, if you really do not know what to do, then in that case you simply use ReLU, and that's why I said it is used in most of the cases and is the most popular activation function. Then if your output is binary, that means two classes like cats and dogs, email spam or not a spam, or whether a person is going to buy an insurance or not going to buy an insurance, like that, then in that case sigmoid is the natural choice. Then there will be a demo related to the working of ReLU, so how this typically works. So we will see this as part of a separate video. So that's essentially about the two things that we have seen as part of this video, that is optimizer, and I explained to you the optimizer. Then apart from that, we have explained about the various activation functions. I hope you like this video. Thank you. So now ReLU I can write in the script wise also. Okay, so I can simply have a Python script and then I can explain you how it is working. So let's say I have written a ReLU function. This is my ReLU, that's why it is called as my ReLU. And then we are just checking, obviously we are using it for two-dimensional array, so we are just checking whether the shape is 2, and then we are just ensuring that x is protected forward. So we are using x dot copy function. I have told you about this earlier. Then we are just having a loop, and what we are doing, you can see it. So for in the inner loop we can have xij is equal to max of, so this is the function that we are using, max, and then we are capping it to 0. And let us say that I'll just quickly run this, and then I basically initialize y to the array, and now I call z is equal to my ReLU, and I'm passing this two-dimensional array where you can see there are some few negative values are there. Okay, so I will run this, and now I will run this z. Okay, so now you can see this z happens to be now 0, because now this particular value is made 0. Similarly, this 35 has become 0, and then here minus 2.8 has become 0. Okay, so that means what I have achieved is actually this particular behavior where I was trying to explain you that I am basically capping you. So you capping the thing. So this is that negative values basically are capped at 0, and then from 0 onwards I get the value. So that is basically the ReLU that we have seen. Okay, so that's what we have seen in today's presentation. Hi everyone, welcome to Deep Learning tutorial series. For today we are going to look into loss functions. That's the topic for today's video. I hope you are liking my videos. If you have any comments, please share those comments at my email ID, that is smltech16@gmail.com. and obviously, and another request is basically try to subscribe to the channel so that you will get all the latest videos that are getting uploaded, and all those videos essentially are in a sequence, so hopefully it will help you in understanding this topic, that is deep learning. So for today, as mentioned earlier, we are going to understand what is loss function. So let's get into that. So up to now we have considered Keras, then we understood ANN, then we understood optimizer. So these are the three main topics that we have seen earlier. As part of Keras, I have told you a brief about what is Keras and what is TensorFlow and all that. Obviously we are going to use that later, so we will speak more about it and we will do hands-on experiments with that. Then in ANN we have seen about the layers, then the backpropagation algorithm. In the optimizer we have seen about the functions that are there. Apart from that, we also have seen the gradient descent. So all those things, three bullets or these three topics are now grayed out, and we'll concentrate now on the loss functions. So as we know, this is the basic slide that we are using, or this is the diagram that we are using, where we understand the layered approach that is there in the deep learning, and then there is the predictions, and then the true target. So then there is a loss function, and we get the score, and that particular thing is communicated to optimizer, and then the weights are updated. So that we now know this, and where this backpropagation algorithm fits, then how the chaining of derivatives happen. So these things we have seen in our previous videos. Those people who are directly jumping to these videos, I'll recommend please take a look at those earlier videos. So having seen this diagram, now the concentration will be on the loss function. Okay, but this is that loss function that we are interested in, because earlier we have seen optimizer. So now we are going to see the loss function. So when we talk about loss function, why do we require that? So it's a common sense, we have seen this. So loss function helps in optimizing the parameters of the neural network. So when we talk about parameters, probably I would have mentioned it earlier. So you minimize the loss for a neural network by optimizing its parameters. And when we talk about parameters, so we basically mean by weights, because that's the way weights are going to control my behavior of the layer. So loss function is helping me to optimize the parameter, that means weights of the neural network. So now we know this. Okay. So essentially it is going to measure the inconsistency between the truth and the predicted value, that is y dash. Okay. So now the robustness of the model, that means the model, whatever the neural network model that I have defined, so that will increase along with the decrease of the value of loss function. That is again a common sense, because more the closer I am to the truth or to the actual, then my robustness, then I can very well say that my model is correct and it's robust one. Okay. So we have seen that gradient descent method is used to optimize the weights of the network such that loss is very biased. So do that basically. So we have to understand a concept or a terminology that comes typically in communication, that is electronic communication. Typically they have a concept called as entropy. Even in computer communication people will study that. So entropy is one such concept. So entropy refers to the relative degree of randomness. Now probably you will feel that is it a just a sudden a break or a sudden change of topic that has happened from where I was talking about loss functions and then the robustness of model and all that, and suddenly that entropy terminology has come. The reason is that because we are interested in the loss, okay, and how closer or how far we are from the truth, okay, that is basically the important thing. So the entropy aids me to do such measurements, okay. So it will become clear now as we proceed. So what is entropy? It's a measure of average information content per source symbol. Now this is a definition that I have quoted, the way in which it is basically told in the electronic communication literatures, okay. So essentially entropy refers to the relative degree of randomness. That means suppose if I have 8 bits and so I want to measure the degree of randomness, so I will use how many and if I am trying to send those, say for example 8 bits, then I will use that to measure the degree of randomness that basically at the receiver end, okay. So here obviously we are not going to do such thing, so we are basically going to concentrate on the cross entropy, okay. Now that's where the why is it like that, because now you have y, that is the truth, and you have the predicted values, so you require something. So cross entropy will be used to quantify the difference between two probability distribution. So this is again a terminology that is coming from the communication. So this terminology or this cross entropy will be used to quantify the difference between two probability distribution, and we are going to get that, and as we use Keras in our next video, I will be demonstrating that, and you will see how this probability distributions are generated, okay. So for just now, for the sake of understanding, we have two values, that is y and y dash. So we need to measure how we need to basically make use of those two things, and then we need to measure, okay. So let's understand what exactly we mean by cross entropy, because otherwise it will not be clear, okay. So suppose if I have a specific training instance, and suppose let's say I have I am training a particular this one, okay, a particular sequence or a particular data, okay, and I know that of the three, let's say that the label is B, the actual answer is B out of the possible A, B, C. So how do I put it? Let's say that I have a class basically, and in that class, let's say there are 3 students, say A, B and C, okay. So these are the 3 names of the people, and I know that B has stopped it, okay. For example, B has stopped it, okay. Now if this particular situation is there, then there is a probability that A also can be closer to the first rank, C also could be closer to the first rank, but basically for B the correct answer is actually B. So that particular thing is referred as, say for example here, label B, okay, because we will come to this terminology of deep learning later, but typically it will be called as label, okay. So now we know that of these 3 students, there are 3 students and the answer is actually, the correct answer is B. So the true distribution from this training instance is, in our example is, that means the probability, now the final answer basically means, though there is a probability that A was closer, C was closer, that's not the point. The point is, now here we know that B is the right answer. However, that means A has not topped, and that means C also has not topped. Okay. So the DL algorithm, how is it going to predict? Obviously, it is not going to predict that A has basically got 0 marks or C has got 0 marks. Okay, it's not going to do that. So what it is going to do? So it is going to predict something like this. So probability of A is, say for example, 0.228, then probability of B is 0.62, and then probability of C is, say for example, 0.15. Okay. Now that means what we are going, now we are going to use this cross entropy, and then the cross entropy loss is going to determine how close is the predicted distribution to the true distribution, and that is where this comes. So now the true distribution is basically, for class B is probability 1. So but however, the probability for class B as predicted by the algorithm is close to 0.62. Okay, so that's where this cross entropy comes into picture. So let's proceed further. So now, as part of this cross entropy, there are further functionalities or further subtopics, I will say, which are available. So first is a binary cross entropy. So cross entropy is a default loss function to use for binary classification. That means whenever I have to make a decision, say yes, no, 0, 1, like that, then I am going to make use of, obviously cross entropy will be there as part of the loss function. However, I am going to make use of for binary classification, where I have to decide. Okay, so it is intended for use with binary classification where target values are in the set 0 and 1. Okay. Then there is another thing which is called as sparse categorical cross entropy. Now all these things will become clear as we proceed with the examples or when we do the hands-on. Okay. So example for binary cross entropy, when will I use it? Suppose if I have, let's say, two set of images. Say suppose if I have one set of images where I have various photos of, say, horse, and let's say then I have another set of images, say, which is basically of cow. Now when I have photos of horse and photos of cow, and I have, let's say, some thousands of such photos, say maybe 5,000 photos of horse and say 5,000 photos of different cows. Okay. Now if I want to classify with very good amount of I will say accuracy, then in that case I require a cross entropy, and that particular thing I will be using a binary, because the decision is binary whether it is a horse or a cow. I am not interested in whether which type of horse breed or something, but here it is intended as it is whether it is a horse or whether it is a cow. So such type of situations are an example where I will use a binary cross entropy. Then I have another situation where I have to choose amongst different images, say for example. So that particular thing or different set, so that is typically called as a multi-class classification. So in that case I will use sparse cross entropy. So predicting, say for example, if I were to predict words in a vocabulary, may have tens or hundreds of thousands of categories, so one for each label, then that is an example. Or let's say we have different categories of clothes. So categories of clothes can be like, for example, I have cap, I have, say, t-shirt, I have, say, pullover, I have, say for example, shoe, and all that. Okay, so how do I predict from amongst the different classes of categories? Okay, so in that case and I will be using such type of thing. So this is basically sparse categorical cross entropy. So just to give you an idea, there are several such loss functions are there. We are obviously not going to go into all those details. So just I have told you the those important things. So important things typically we will be using will be, say, binary cross entropy. Another is a sparse cross entropy. So this is called a sparse multi-class. Okay, there are other things also, you can always play with it, but these are some of the very popular loss functions that are there. So what is now going to be next? After now we have understood what is artificial neural network, we have seen what is backpropagation algorithm, we have seen what is the chaining of derivatives, then we have seen optimizer essentially, then we have seen gradient descent, so that we have done, then we have seen what are the different activation, what is activation function and what is mean by activation function and what are the different types. Now we have seen what is loss function, what it is responsible for, and what are the different types of loss function. So now having done all this, so now we are ready to start doing or start using Keras, and that means we have to do hands-on using Keras. So that we will cover in the next video. Hello friends. So as part of getting started with respect to Keras, we now need to know the installations that we should have on our system. So let's understand that. So for that I will take you to the Jupyter and I will explain you the installations that we require. So let me now take you to Jupyter. So here you need to install the TensorFlow. So that can be done by using a command which is pip install TensorFlow. And then you can make use of TensorFlow by saying import TensorFlow. So let me just run this command in front of you. So it will take some time so that this star goes away and it basically successfully imports the TensorFlow. I already have done installation of TensorFlow on my system. Then we can import the Keras because we are going to make use of Keras library. So here let me just run this line and now I have also imported Keras. So now we can just get an idea of version of Keras as well as of the TensorFlow. So you can see here keras.backend function tells me that TensorFlow is now my backend. Now to know the version of Keras, we just need to know keras dot underscore underscore version underscore underscore. So this can be done quickly by just saying keras dot, and then if you just do tab, then it's going to give you a lot of help. So it obviously it will come little later. So you just make use of this option and then just say underscore underscore version. So it's going to give the version. So that means on this system that I'm currently showing you the demo, the Keras version is 2.8. So obviously we are going to make use of the TensorFlow because as part of TensorFlow there is a Keras and that is what we are going to use. So here the version also of TensorFlow will be 2.8. So essentially it's the TensorFlow version that ideally we should check, and then obviously Keras is part of that. So that's why we have done here from TensorFlow import Keras. Then if you want to have a data set from Keras, then you can just do it by saying from tensorflow.keras.datasets, and then you can import some data set, say for example here fashion. Now apart from the TensorFlow and Keras that we require, we also require NumPy. So I already have installed NumPy on my machine. So here let me just show you the version of NumPy that I have. So here it is 1.22.3. Similarly, then you require matplotlib so that you can always install on your machine, and then you can make use of matplotlib. So these are some of the basic things that you require typically when you use it when you do the deep learning activities. So I hope now here you basically have understood which version of TensorFlow and Keras is on this machine that we are using. Thank you. So we have seen this diagram that we have used it. So as a part of deep learning approach, there are layers, then there is predictions and the true targets, and then loss function, then the loss score, and then the optimizer, which is essentially controlling the weight update. So you know that. So now having with this knowledge, so now we know that we now need to work on few things. So what is important is now the data, then the layer. So data layer, that's basically you have to do, and then apart from that you obviously have to figure out what are you going to do measurement, how the training is going to happen and stuff like that. Okay, so that means there are multiple things. So data, model, that is layer or the model, and then the other thing. Okay, so let's now get into that. So that is basically called as workflow. So Keras workflow. So need to define the training data, that means input tensors and the target tensors. Okay, because I have told you what is a tensor and all that, and we are all going to work with tensor. So we need to define the training data, that is going to be input tensor and target tensor. Then you need to define the network of layers, and that's what I said as part of deep learning introduction. So that means we are actually going to define it as a model which is going to map inputs to target, because the model is responsible for doing the job of mapping. Then configuring the learning process, so that's a very important one. Now since you have defined the model, now next things comes is you need to actually choose. So what will you choose? You are going to choose a loss function, and that's what we have seen in our previous videos. You need to choose a loss function, you need to choose an optimizer, and then you also need to have some metrics which you are going to monitor, because otherwise how are you going to keep track of it? So you need to do the configuration of these three. So the basic is you have to have data, that means input and target, because only then you can train the model. That's why it is called as training data. So for this input, this was the output. For this input, this is the output. Like that, you basically are going to get data, and then you basically are going to define your own model, and then you are going to configure it. Once you have done it, then you are going to iterate on the training data, and that particular thing is called as fitment, or it is called as fitting. So you do that using the fit method of your model. Okay, and that's the beauty of Keras, because Keras provides me to do this all these things which is relevant or which is required for doing the deep learning examples. Okay, so you are going to iterate on the data and by calling or by making use of the fit method. Then after that you are going to evaluate it. That means you can use another data or you can evaluate how my model is performing, so that is optional. And then obviously you are going to use it for doing predictions, because suppose if I have trained it on say some sample, say a sample, now I want to predict how the B is going to behave. So in that case I am going to make use of the predict facility also. So these are the steps. So essentially there are 4 steps, that is define training data, then the model, then the learning process, that means configuring the learning process, and fit. So these are 4 basic or the must have type of this one. Then evaluation and prediction is depends on which one you want. You may want both, or it depends on your interest for that example. So now when it comes to defining the model, typically Keras provides you with the 2 types of model. So first one is called a sequential model, or it is basically it comes under sequential class. So normally you use this when you are going to for linear stacks of layers. So this is the most common architecture, because you tend to define one layer, that is something like you have one stack or one layer, then say stack of books. So one book on the one first book, then there is a second book, then there is a third book, like that. So that means whenever you are going to have linear stacks of layer, we tend to use the sequential model, and this is the one of the popular model. Apart from that, there is also a functional API, and this will be used where you are going to define a completely arbitrary architecture. That means you are not restricted by the linear layering, but you can have basically it is called as acyclic graphs of layers. Okay, so technical name is that. So you can have your own arbitrary architectures. Okay, so we are going to obviously use sequential class as part of our exercise, because that's one of the popular model, and it works quite well. Okay, so we will now get into that. So let's now see it doing it or using it hands-on. So the example that we are going to do is basically we are going to use fashion images and you are going to do the image classification. So now from where this data set is going to be available to us. So essentially Keras also has a data set information or data set rather available. So it has multiple data sets. So of that data set we are going to use the fashion images. So now in these images you can see there are basically images of say boot, ankle boot, then this is like a pullover, this is again an ankle boot, this is like a sandal, then this is like say for example pullover, yeah, so this is like a pullover. So then this is like a t-shirt. Okay, so you can see this is a t-shirt. So these are all this one. So typically whenever you have the data, it is basically provided like as a index and then the label. So typically it will be called as label description. So here you can see t-shirt is a label description, then trouser, then pullover, coat, dress, coat, sandal, shirt, sneaker, bag and ankle boot. So this is called as label in with respect to label description with respect to the DL terminology. So now as part of the hands-on, what we are going to do is we basically are going to classify using this jumbled up data. You are going to, that means the fashion images, we are going to do the classification. So for that we need to add an input layer, then we add a hidden layer. Okay, so hidden layer is also called as dense layer. So we'll see this quickly now, and then we are going to do the output. We are going to add output layer. So then we are going to compile. So this is more like defining the model. Then we compile, then we fit model. That is what I have said. So compiling is basically the way in which write any program we compile so that there are no errors in that. So something similar. Then you do the fitment and then you use it to doing prediction and then you can do evaluation. Okay. So that's basically the hands-on activity. So hello friends. So now we will take a look at demonstration and we will understand how do we make use of Keras. So as part of this demonstration as mentioned earlier, we will basically make use of a fashion database where we have various figures or images of clothes and they are like boots, t-shirts, then pullover like that. So there are various things you can see it here like trousers, pullover, coat, sandal and all that. So essentially there are 9, rather 0 to 9, that means 10 labels are there, 0 for t-shirt oblique top and then 9 is for the ankle boot. So to do this image classification, we are going to add a input layer, then we will add a hidden layer and then we will add a output layer, and then once we have done all these things, then obviously we need to compile it, then we will train the model and that basically will be called as fitting the model, and then we will use it for doing prediction and evaluation. So before we go into the program, let me just recap this activity. So when we are going to define the model, that means first obviously you require a training data, so that anyway I will explain you or we will see how to do that, and that is a fashion data. The main thing is that you are going to make use of a model and then you need to configure that. That means you need to configure the learning process and where you are going to choose the loss function, then an optimizer and the metrics that you want to monitor. And then obviously you are going to do the training, that means you are going to do the iteration by calling the fit method, and then after the training is over, you can use the model for doing the prediction or evaluation. So that is in general the Keras workflow. So now let's see that in action. So let me now take you to the program. So for this program you require a NumPy support. So let me just import NumPy. Then we require matplotlib. So I am importing matplotlib. Then we require obviously TensorFlow. So I am importing TensorFlow. And then from TensorFlow we require Keras. So let me just do that here. So and then we can just check that okay, the backend for Keras is a TensorFlow. Then we can check for the version. Similarly, we can check for the TensorFlow version. Now once we are done with this basic sanity or the basic understanding, now we need to import the data, and that data is available as part of Keras dataset. So what we are going to do is we are basically going to import the data, and which is a fashion data. So it is called as fashion underscore MNIST. So from tensorflow.keras.datasets, we are going to import the fashion MNIST. So once we have done this, then we now need to load this data. Now what exactly happens is when you do this, then typically it takes time. However, for on my machine, this particular thing is already done. That means this downloading of this dataset. Otherwise, this dataset is available at https://keras.io oblique datasets. So it downloads. So depending on your network speed, it takes some time and it typically will download into C users and then whatever the name of the user that you are logged in, and then there will be a .keras folder and then the data sets. So let me just show you here. So here if you look at it, see users and then the username and then there is a .keras. So you can see there is a .keras data set, and in that fashion MNIST, and in this we are interested in train and train images and train labels. So these are the labels are like the names that I told you, like t-shirt, pullover and all that, and these are the actual images. So this is what basically the thing is. So now we will use this function load data, and this load data is going to load this data which is essentially a trained data and a test data. So it's going to create that trained data and test data, and it has loaded that. So once it has loaded this, then we can take a look at the shape. So now we can see it's a 28 by 28 image. Each image is of size 28 by 28, and there are such 60,000 images are there. Similarly, test images are again 28 by 28 each image, and there are 10,000 samples. That means 60,000 images can be used for doing training and 10,000 images are for doing testing. Similarly, Y train we can just look at it, and here you can see it's a 60,000. Why? Because there are six for corresponding to X train, there are 60,000 Y train, which essentially are just an array. So you can see this information. You can, if you click on this, you will see this. I just copied it. So https keras.io.datasets, and there you can see there are basically label description like 0 is for t-shirt top, 1 is for trouser, 2 is for pullover, like that till 9. So 9 is a ankle boot. So this is what basically. So that means now what are we going to do is we are going to train using these 60,000 images which are part of fashion MNIST, and then we are going to test for the 10,000 images. That means of any one image or any two image we can select, and then we can just check it and we can test it essentially. So that is what this particular thing is about. So now to give you an idea, we can just take a look at the image. So if I just do x train 0, that means the zeroth image, then here it is, you can see it's a ankle boot. So this doesn't mean that it is zeroth index, it is not zeroth this one, this is the label. So you can see it here, and corresponding to that we can say y train 0, and then it's going to show 9. So you can see this 9 is ankle boot and it corresponds to the image also. So that's what I told you. So this is the index, and corresponding to that it's a ankle boot. Similarly, we can just select some one, and then which is a pullover, and then for that corresponding to that it's a t-shirt or whatever. Okay, so it's a t-shirt. So 0 is a t-shirt. So like that we can basically play, and we can just plot some few random images. So if you want to put some 10 here, so we can just put 10, and which is something, and for that corresponding to that we will have to put here 10. So then it corresponds to again a t-shirt. Okay, so that's what basically it is. Now if I want to change it to say 17, so let me run this. Yeah, so again I think these are all t-shirts. Okay, so let's put some random number. Yeah, so this is something different. Yeah, so this is 2. 2 is now pullover. Okay, so it looks pullover. Yeah, so that's what essentially we can play with it. Now what we want is that now this particular data is from 1 to 255, or rather 0 to 255, not 1, 2 to 0 to 255. So we would like it to be normalized. So we are going to divide by the maximum value, which is essentially 255. So we are going to divide train as well as test by 255. So now this x train and x test are basically the values between 0 and 1. So you can see now it's a essentially it's a three-dimensional array. That means 60,000 entries, and each entry is of 28 by 28. That's what is shown as a this particular matrix is 28 by 28. So like that, so similarly we can see the test. So once we have seen this X train and X test, now we are going to build the model. Now as I explained to you in the slide, so this is very important. So we are going to define a network model or model, and then which is going to help you map inputs to the target, and then you configure the learning process by choosing a loss function, then optimizer, and then the metrics to monitor. And once you have configured this, that means you have defined your model, rather you have defined the model and then you have configured it, then you basically are going to do the training, which is basically by calling the fit method. So let's now do that. So here we are going to import keras.models sequential, and similarly we are going to have the layer. So let me just tell you this. So this from keras.layers we are going to have dense layer, then the activation support you require, and then we also require a flattening support. So let's use this one by one so that it will become clear. So first is our model. So model is a sequential model. Then we first add the, that means you add a layer, and that layer, first layer is a you are going to take the input which is of 28 by 28 shape. So you are going to flatten it, that means now it will, by doing flattening, that's why you require a flattening support. So you are going to form a one dimensional array. So this uh, uh, 2D array will be converted into 1D array, that means 28 by 28, which is 784. So you are going to have a one single array of in entries 784. So 784 neurons in the input essentially. So let's run this. So this is your first layer. Then you add a dense layer. Now in the dense layer you basically require a you start with random number, so you can do with some 20 neurons. You can play with this later. You can have 20,000 or other 2,000 neurons also. So let's say that I want 20 neurons, and which is and the activation function that we are going to use is ReLU. That's why we have added here activation layer, support for activation. So here we will start with the 20 neurons. So we have added a fully connected layer, which is a dense layer where there are 20 neurons, and which is going to make use of activation ReLU. Then we are going to have another dense layer, and here the number of neurons are 10. Why 10 are there? Because you are going to have the labels like t-shirt, pullover, boot, ankle boot, sandal, like that. So they are basically 0 to 9, that means 10. So that's why you are going to have number of neurons as 10, and then obviously it's going to be a you need to classify. So that's why you are going to make use of softmax, which is going to distribute into the different classes. So I have told you the activation is will be here used as softmax because it helps you to distribute into different classes, and here we have 10 such classes. So let's execute this. So that means now you have a model where you have added the first layer, which is a flattening, then you added a second layer which is a dense layer, and the third layer is where you are going to decide. So then with the softmax as the activation function. So we can just quickly take a look at summary. So you can see this is a flattening layer where the shape is 784, then dense layer where we have used 20 neurons, and essentially it has boiled to some parameter which it has computed. And then the dense layer again, here we have 10 neurons. I told you the 10 is because we have 10 labels, and then it is going to have the parameter which is corresponding to 210. So total parameters it has told, then how many are trainable. So here everything is trainable, there is no non-trainable params. So then we are going to do the compilation of the model. So for that we are going to make use of the loss function. So loss function is similar to the one used in the gradient descent. So here we are going to use the loss function as a categorical cross entropy because we need to correlate. So and it's a sparse categorical cross entropy. So that was explained to you as part of loss function. Then optimizer is a when you train your neural network model. So essentially it's an algorithm. So we are going to make use of the algorithm which is Adam algorithm, which is essentially it's a improvisation over the gradient descent method, and that algorithm helps you to adjust the weights. So and which essentially are going to adjust the neurons weights of the edge neurons. and then you have the metrics. So here we are going to measure the accuracy. So then we are going to do the fitment. So for that we are going to provide train and X train and Y train, and here by default it's going to run for one epoch, otherwise it takes good amount of time. So here you can see the accuracy is 80%. If you improvise on epochs, obviously it will get improvised. Similarly, if I just run it for 3 epochs, then you can see it is taking time, little more time, then obviously we are running it for 3. And here the accuracy earlier was 84, then 85, 86, like that. So you can see this loss is decreasing and accuracy is increasing. So we can now take a look at this image which we are going to give it as a test. So now that means our job is done. We have trained the model for 3 epochs. Now we will test it. So before testing, let's take what we are going to give the image. So this is x test 0 is a boot. So let's give this which is a, then x test 1 is a pullover. Okay. So the shape is 10,000 images 28 by 28, I told you already. So let's now do the prediction. So we will predict it. So let's see the first image YP0. So now what is happening here, you will see there are 10 probabilities are given. So this is a probability across different classes. So here we have 9 classes. So now we require a maximum of this number. So for that we are going to use a numpy function which is argmax of YP0. So it's 9. That means 9 is whatever. So let's see this 9. So YP0 is 9. Let us see it for YP1. Similarly, argmax YP1, and then it is 2. So let's see this 9. So 9 is a boot. Yeah, so this is a boot, ankle boot. So let's go up because we have seen this earlier. So yeah, so 9 is an ankle boot. This is correct. Then let's scroll down. YP1. So what was YP1? YP1 was 2. Okay, so 2 is, uh, let's see what is 2. 2 should be pullover, I believe. Let's see. Yeah, so 2 is pullover. So like that we can test it with some input images, various input images we can give. I'm just scrolling it down, it doesn't matter. So right that we can test with some X test because we have 10,000 images. So till 0 to 999, that means till 10,000 we can check for any other input, and corresponding to that we should obtain a Y, and then we can check whether it is correct or not. And before doing that checking we need to do the argmax so that it gives the maximum value, which tells which is the index is the highest, which corresponds to whatever the ankle boot and all that. Now once we are done we can do the evaluation. So for that we can simply do the evaluation by doing X test and Y test. So you can see it here, it is the accuracy is almost good. So it is like 0.85 is the accuracy. Now the question is, do I need to basically use the only 20 neurons or something which were part of the hidden layer? So we can play with that. So suppose if I want to, instead of 20 I can say, for example, I will just comment out this and say probably I will do it here, say 200. Then I can once again have a model, then I will first flatten it, then I will call dense, then dense, then we can see a summary. So you see here the summary, though it has increased, so this has taken more space now. Then we can compile, then we can train it for say 3 epochs. I'm just directly going to 3, 83, 86, and now you can see it is almost 88% roughly. Yeah, it is 8793. And then we can once again test it. Similarly, we can test it. Then we can do prediction. Obviously it's going to work because we have increased it. Now let's see the, so here you can see this accuracy is little better than the one which was earlier, it was 85%. So here it is close to 87%. So like that you can play with this number of neurons, and you can have your model which basically fits as per your, or which is as per your requirement. So I hope you like this demo which was essentially about this hands-on activity and how do you carry out the image classification. Thank you.
Hi friends, welcome to Deep Learning Tutorial Series. As part of this video, we will understand Introduction to Functional API. So as part of this topic, we will basically understand little more about functional API. So in general, we'll try to understand what's there after sequential model. Then we'll try to get into introduction to functional API. And then we'll try to see, or we'll just try to get an idea about what are the different models. So let's try to get into what is beyond sequential model. Now why this topic has come is because up to now we were using neural network, we were basically creating the model, we were defining our own model and stuff like that. So when we were doing that, so we were using sequential, like we used to make up the constructor sequential and we used to basically get the model object. So that is what basically the sequential model we have used. So now here when we make use of a sequential model, then essentially it makes the assumption that the particular network has exactly one input and it has exactly one output. So that's the first assumption. The second one is it is going to consist of linear stack of layers. That means you are going to define layers as per your requirement and it's going to look like this. So that means you have an input and then you have an output and in between you basically are going to have linear stack of layers and you are going to get the output. And here the input is exactly 1, similarly the output also which is exactly 1. Now is this good enough? So yes, to a certain extent we have solved up to now and we have applied it. However, when it comes to that, there is a limitation and that particular limitation is this assumption now becomes inflexible for some networks oblique model. The reason is because you are going to require, there are cases where you require independent inputs. There are cases where there is going to be multiple output or there are going to be multiple output. And then apart from that, whatever the network that is part of processing or that you are using, it can have internal branching between the layers. That means you are going to have layers and in between you have, or you may require a sort of situation where there is going to be an internal branching. So this is something like graph of layers instead of linear stacks of layers. So instead of linear stack, now you are trying to visualize this overall approach or overall these bullet points is more like graphs of layers. And that's where this topic comes into it, that is multi-input model. So multi-input model basically now is going to cater for a case where you are going to merge the data that is coming from different input sources and then processing each type of data using different kinds of neural layers. So here now we are talking about a case where you are going to have multiple input. Why we are dealing with multiple input is because the point I just told, because if I use the sequential model, then I am basically having a situation where it's an inflexible with respect to the input and output, because one input one output as well as the layers are going to be the linear. Now there are going to be the cases or there are going to be situations where you require to take inputs from multiple sources or different input sources. So you require to have a facility where you can do merging of the data. Then the processing of each type of data using different kinds of neural layers. Now some tasks require merging data coming from various sources, as I was basically mentioning. So that is where the multi-input model comes into picture. So let us try to understand this point with an example. Let us say you have collections of old printing and you basically want to predict price of old printing. Now here when you talk about old printing, then obviously when we try to understand it, then you are going to have the age of the painting, because that is like how old the painting is or to which era it was belonging to, stuff like that. So that means you basically are going to have age of painting as the metadata. Similarly, who was the painter, because that also plays a very important role. So it is part of metadata as explained in the slide. So metadata, these examples are age of painting, painter, like that are the metadata examples. Then there will be a text description. There can be a text description of the about the painting, or maybe about the context or whatever. So there is going to be that, and then the actual picture or a painting. Okay, so that means now if you want to basically come up with a price, or you want to predict the price of old painting, then you basically are going to get the data or this information from multiple, as part of multiple inputs. So to deal it, if I want to deal this information separately, then suppose if I would have got say metadata, then probably what alone metadata, then what I would have done is I would have just made use of say one hot encoder which we have seen as part of our earlier videos, and then I would have made use of a dense network. Then if I want to deal with text, so then I would have used say RNN, can be one such approach where I can do text processing, and we have seen that as part of our again previous practical hands-on and stuff like that. Then if I want to deal with picture, then convolutional networks like 2D convex obviously play the role. However, that is not the point here. The point is because we are not going to do the processing independently, because there is all the three together is going to give me some information which just a picture will not be able to give me, which only metadata processing will not be able to give me. Similarly, text processing. So this cannot be the approach. So we need to deal it jointly. So that is where the merge module comes into picture. So that means you now need to learn jointly. So now you can see it. So you have this in the diagram as shown. So you have this metadata which is fed to the dense network. Then that is one hot encoding followed by the dense network, and then you have an RNN module where it is the text is processed or text is given, and then ConvNet where you are giving the actual picture or photo, and then you basically are having a merge module or a merging module, and then the output of that is basically going to be the price, and that was the example here, like predict price of old 20. So this is one such scenario where you are dealing with a multi-input model. Now the way in which you have multi-input model, you are also going to require to handle a situation where you need to do predict multiple target attributes of input data. That means you can think of a multi-output model. The example is, suppose let's say there is a short story or a text basically. So example is, now you need to classify that text or a short story, like you need to tell the genre of that, and then predict the date of the story. So suppose if it is a short story text, then you need to identify if it is a horror story, or that, or whether it is a romance, or whether it is other things. So that's the way you need to do the classification. So that is the thing that you are going to do from the text. And another point that comes up actually is that genre and date are interrelated. Now you probably can very easily guess, like we say that in 1970s or in 1980s, like that these type of movies used to be there, or these type of novels, or these type of stories people used to write. Then probably in 80s some other type of stories were playing the dominant role. Then say in 90s some other type of stories. So the point here is genre and date are interrelated. They are not independent. So you require a model to jointly predict both genre and or gen and date at same time. So genre and date at same time needs to be handled. So model will have now two outputs. So you can see in the diagram you have this merging module where the text is fed, which basically is the text of the story, and then from there you basically are going to process through dense network. You probably can deal with genre, and then the other one is the date. Probably you can use that and try to work on it. Now here we are just trying to show this diagram as an example. This is not like this is the way somebody is going to do, but this is one such thing that typically people give it as example in literature. So now up to now we have basically understood like the types of models or the overall approach when we try to deal or when you require to deal is like where you have a multi input model and another is a multi output model. So now having dealt these topics, like we need to go beyond say sequential model, then what was the need, so that we have understood because of inflexibility and stuff like that. Then we understood little bit about the multiple input as well as multiple output. So typically the trends that people work with respect to advances in this area as part of neural network architecture. So typically they deal it will be like graph like networks. So you are going to have neural networks requiring non-linear network topology, where networks are structured as directed acyclic graphs. So some examples are there, like Inception family of network, which is developed at Google, which is going to where the input is processed by several parallel convolutional branches and outputs are then merged back into a single tensor. Another example is a ResNet, where they are going to add residual connections to a model, and it is developed at Microsoft. So these are just I'm just mentioning in the slide because we are dealing with an introduction to functional API. So this is just to give the viewer or the person who is going to watch this video the further things or what is lying when it comes to the graph like networks. So now we'll go as part of this video. Let's get into because having understood the multiple input, multiple output and all that, so we have seen this, then we need to go beyond sequential model. So that's where the intro to functional API now fits into it. So we need to get an idea about it. So when we talk about functional API and just an introduction as a part of introduction, so where we are going to now directly manipulate tensor. So that is the first feature or a point as part of the functional API. Then we are going to use layers as function. Now this point is extremely important. The reason is because now the layers are going to behave like as if they are functions, and they are going to take tensors and return tensors as output. That means the input is a tensor and output is a tensor. However, the point is up to now we used to define layer. However, now here the layers are going to work as function, and that's why this topic is titled as, or this area of in deep learning is considered as is named as functional API. So this is a very huge topic, functional API. We are trying to get into the introduction part of this as part of this tutorial series. So how do I basically make use of this approach or make use this? So again we are using Keras. So from Keras we are going to import input, and then we are going to import the layers. Okay. So as I am telling, layers are basically are going to be as function. So the first thing is you basically try to create a tensor, say of some shape 32 here. This is just an example or a placeholder. So here input we are going to input tensor. Then we are going to basically use layer as a function, and that is what this second line is telling. So dense is equal to layers dot dense. Then this is activation is equal to ReLU and 30. So here we are using, the point here is we are using layer is a function. So that is what is important, and then we are going to get output tensor. So here we are giving to this dense, that means a layer, this is the object of the layer. So layer called on a tensor and it returns a tensor. So you can see this. So now dense object. So the second line we have just formed the object where we have used the dense layer, and then we are using this dense layer which is basically taking input as a tensor, and then again it returns the tensor, which is here denoted or mentioned as output tensor. So we will basically take a look at functional API introduction demo. So to those people who have reached our deep learning curriculum up to this point will get an idea basically what is a functional API, and then as part of further research they are basically given some input about the trends. As part of the trends they can always look into it, then they can go more into details about say multiple input, multiple output, and then stuff like that. So let's take a look at this functional API introduction, so that the concept about functional API will become clear. So let's go to that. So we'll go to Jupyter. So we are obviously importing Keras. So we have imported the Keras. Now from keras.model. So now we need to understand this concept very clearly. Why? Because what we are going to do as part of this demonstration is we are going to form a sequential model, because up to now we were only using sequential model. So we will try to form a sequential model, and then we will make use of functional API and see what is the equivalent model. So that way we will learn how this approach, that's why this video is titled introduction. So we are just trying to introduce the concept of functional API. So here you can see from keras.models we are importing sequential, and then you can see we are also importing model as a general one, because we never up to now did this. So we were always using sequential, but however now we are importing model, then we are importing layers, and then we are importing input. So we are now going to first form a sequential model. So we are basically creating the object sequential model. Then in this, because this we know we are doing this all along in various videos as part of this tutorial series. So we will add a layer. So here you can see sequential model dot add, and we add a dense layer dot dense, and then with whatever the this number, and then activation ReLU. Input shape is going to take say shape 64. So then the 32, and then say the dense layer, third layer is the 10, where you have the softmax activation. Let me just run this. So we have created a sequential model here, and we are used to this. Now suppose if this is the general way, or this is the way I was up to now defining it, then how can I basically use a functional API? So let's try to understand that concept. So we basically will form an input tensor. So let's the shape will be now 64 here. So here that's what basically we are trying to do. So this is the 64. Then we are now, you can see the way in which I am doing it now. So this is input is equal to input tensor is equal to input, and with the shape. Now we are why? Because we are doing a functional equivalent model. Then we are just giving some temporary, sort of like a temporary variable name or a temporary name x, and then we are saying layers dot dense, and then here we are basically giving two layers we are adding, so 32, and now you can see the input to this layer is now is basically, you can see the way in which it is. So layers dot dense, and then input underscore tensor. So we are now relating this x, that is this some x here, where you have layers dot dense, and then input tensor also plays a role here. Then x again here. So now this x is used as input here. Okay, so layers dot dense, and then so it's more like using this. So you are forming this x by using dense layer and input tensor. Similarly, this x is using layers dot dense and the previous x. So this is that previous x which we are using here. So this is very important. We need to do it in bracket. Then the output tensor is layers dot dense, and then obviously the dense layer definition 10 activation softmax, and then this x, that means this x corresponds to this. So this is the way you try to now have a sort of a graph type of linking, or you are trying to do that. So here now we need to create a model, because here we were very comfortable. We just did sequential model is equal to sequential. We just made use of this constructor. However, that's not going to be the case here. Why? Because now you need to create a model. So here model class, so we are making use of this model constructor. So model class turns an input sensor. So this is that input tensor, sorry. So this is an input tensor and the output tensor into a model. So you can see this model is equal to model. So you can see now this becomes a generic model. This is not related to that it is a sequential model. Why? Because now this is like an input tensor, and this is a output tensor, and it's a model. Now basically takes two parameters here, input tensor and output tensor, and then you get the model. So what is happening here is, this is very important. So behind the scenes, so let me first execute it. So I will execute this, and let me just execute this output tensor, then model. Now what is happening? Let's try to understand it. So behind this scene, because now we have a situation where model, this is the say the functional API model or the model. So model is equal to model input tensor output tensor. So behind the scenes, Keras is doing that job for you. So it retrieves every layer involved in going from input tensor to output tensor, then bringing them together into a graph-like data structure, and that is what is called as model. So that is what in the slides when I was presenting to you or when I was explaining to you. So this is where that graph-like network. So these are all the trends. Obviously, there are so many advanced things I just mentioned you. So this is where basically you have this approach where you are trying to do some connection. So the connection here is general connection we are trying to do, or a simple connection like input tensor and output tensor. So that is what basically the slides I was trying to convey through slide. So Keras is now doing that job for you. It's involved in doing this job, that is input tensor to output tensor, and it's going to bring them together in a graph-like data structure, and that is called as model here. So the reason it works is because output tensor was obtained by repeatedly transforming input tensor. So now you can see this. So that's why I said you need to make use of input tensor. Then from input tensor you transform. So this layer dot dens transformed it to get output as an x. Then use this x and again get an x output, and then you use this x and get the final output tensor. So that is what basically. So reason is that it works is that output tensor was obtained by repeatedly transforming input tensor. In case you have a breakage, or if you don't have that linkage, the way in which here I told you, like in that case, if you try to build a model and from inputs and output and they are not related, then you are not going to build it, so you are going to get a runtime error. So we will now try to run this. So you are going to basically see model.summary. We are going to get this model summary. So I just executed it, and now you can see this input layer. So here the shape is 64, then the dense layer, the 32, 32, 10, and then that's the way you created the model. Once you know how to create a model, that is where the important thing lies as part of the functional API. Then you can study further, and there are trends that are already mentioned in this video. So you can always play with multiple input, multiple output, and dwell more into functional API. So I hope you like this video. This completes our functional API introduction. I am once again repeating, it's an introduction video, and I hope you like this introduction. Thank you. Hi friends, welcome to Deep Learning tutorial series. In this video, we are going to take forward the concept that we have understood as part of introduction to functional API. So in this video, we basically will concentrate on something called as multi-input, multi-output model. The reason to take this topic is because in the last video, we have understood basically there is a requirement of a multi-input. Similarly, there is a requirement of multi-output model. So we'll try to understand this concept as part of this video. So how do I understand this concept? So for that, basically we'll try to sort of simulate a situation. So here we are going to have an idea, or that idea is like you predict how many share of a particular FB post, or you can also say it can be a tweet also. So basically predict how many share of FB post and likes a news headline will receive on say FB or Twitter. So whenever you post it on Twitter or say on Facebook, then let's try to predict how many there can be likes, and then how many basically people are going to retweet. Depends on how you basically consider it. So here it's I'm just trying to tell you, this is more from the point of view of simulating and understanding how basically we deal with functional API and the multi-input, multi-output model. So here basically we will have a situation where there is a main input to the model, which will be the headline itself, because when we are saying that it's a headline which is essentially tweeted or say it's shared on FB, then basically it's the headline itself, so which is actually the sequence of words. Then we'll try to have a auxiliary input, and that auxiliary input will be something like an extra data, such as the time of the day when the headline was posted. That means depending on when the headline is posted, people normally tend to post, say, probably early in the morning, or say in the afternoon, or say in the evening, depend. So the point here is like some auxiliary input or additional type of information is provided, which basically can be considered like a time of the day. Now again I am repeating, it's more from the simulating or understanding how this multi-input multi-output works. So to do this, we are going to have sort of supervision, and the model will be supervised by two loss functions. That means we will have something like two outputs. So in a way you have two inputs. So one is a main input, another is an auxiliary input, and then since you are trying to basically do the supervision, so that supervision will be via two loss functions. That means two outputs is what basically we are trying to consider. So here the important thing to note is the input will receive the headline as a sequence of integer, because we, as part of our previous videos, I have explained to you that basically encoding needs to be done, because essentially whatever the data that you provide, it has to be in the form of an integer. So here basically that we are considering that we are providing the input as an integer and not as a text. So the main input will receive the headline as a sequence of integer, that means each integer encodes a word. So all those details were considered as part of our previous videos. Then this integer value will be between 1 and 10,000. That means we are considering vocabulary of say 10,000 words, and the sequences will be 100 words long. So again I am emphasizing this point. We have already seen as part of text processing videos in this tutorial series, where we actually have seen a similar situation where the integers were used as part of the input, and then the vocabulary we have used of some thousands of words, and then we also have considered some hundreds of words as the sequence. So all those things were considered as part of our handling text sequences. So the concept or that approach continues to be the same here, that means at the basic level. However, now here we are going to do something like predicting, where you need to provide an input which will be two inputs, and then you expect two output where you are going to monitor via loss function. This is overall the idea, or I can say the what we are trying to do. So to do this, basically we have to consider a model. So that model is now multi-input multi-output model. So here we can see in the green, I have shown it here. There is a main input, that is the input layer. Then we are having an embedding layer. Then you can see there is a auxiliary input, and then this is given auxiliary input, and then there is also LSTM. So LSTM, we have seen LSTM again as part of our previous videos as part of text processing. So the output of embedding is provided to LSTM, and then the merge basically is taking input from the auxiliary input and then the LSTM output, and then LSTM is actually providing us a output as an auxiliary output. This is a basically dense network. Then once you have the merge, that is merge layer, then you are giving it to dense 1, dense 2 and dense 3, and then finally there is a main output, again it is a dense layer. So now you can see there are basically there are two inputs, that is main input and auxiliary input, then there is auxiliary output and then the main output. So this is where as part of LSTM you can basically monitor how the output is coming. That's why here it's something like early monitoring in the overall model, and then obviously there is a main output. So this is overall the structure that we are trying to use for this idea, where we have said there is a headline. Obviously the headline we are providing it in numbers, and numbers we are generating. So that concept we should understand about multi-input multi-output. So again I am emphasizing this video or this demonstration that I am going to show it to you now is going to provide you the understanding with respect to the concept of functional API and how we basically can use it to tackle multiple input, multiple output type of situation. So now let's go to the demo about this multi-input, multi-output approach. We'll take you to Jupyter. So here now we can see that this is the main input. So main input we are basically providing a placeholder. So the input is the input layer where we are saying that 100 is the shape, because I told you we are taking receive sequence of 100 integers and then between 1 to 10,000. So I told you it is like the vocabulary we are doing. So we are just creating sort of a placeholder. So type is integer 32 and we can give the name. So here the name of this layer is main input, and that is what basically I have shown here in the diagram. So then we have the embedding layer, again as part of our previous videos where we have used embedding layer and all that, so we know how to use embedding layer. So embedding layer is basically going to produce 512 dimension output. Input dimension is 10,000, then the length is 100 because this is what 100 integers, and then now you can see we have started using this approach of functional API. So here this X is basically embedding, and then the input provided here is the main input. So that means this is the main input. So you can see now that graph is getting created, which I have explained to you as part of our introductory video of functional API. Then we have used, then there is an LSTM. So output of LSTM is basically LSTM is basically transforming this X vector. So that's why you can say LSTM 32 LSTM and then X. So it's going to transform the vector into a single vector containing information about the entire sequence. So again, this is what I am showing you, LSTM, where you are providing the output of embedding and then you get the output. So LSTM out is this. Now we have to basically, so let me just take you there. So you have this two outputs from LSTM, and then auxiliary input is provided to the merge layer. So now we have to basically consider this auxiliary input. So again it's a shape where we are considering 5, here we have considered 100, so it's like a time. So that's good enough, time information, or during the day when that Facebook post comes or say tweet comes, so that is like that. So here we are naming it as an auxiliary input. Name parameter can be used to name a layer. So you insert this auxiliary loss, allowing LSTM and embedding layer to be trained smoothly even though the loss can be high. Okay, so this is that auxiliary input. Then auxiliary output is a dense layer, and activation is sigmoid and name is output, and then it's going to take LSTM out. So that is what LSTM out basically is that. So this is what LSTM out. So let's go here. So you have this auxiliary out. Here auxiliary out. So auxiliary out is transformation basically on the dense layer, and the here we are using the output LSTM out. So this is what LSTM out is. So this is as per the diagram. Then we are actually providing, we are concatenating. What is that we are concatenating? LSTM output and auxiliary input. So these two are basically concatenated, and that's what the diagram was. So LSTM output, so we are concatenating it. So here we are making use of keras layers dot concatenate, and we are providing it as a list. So LSTM out and auxiliary input. So this is what we are giving. Now we have the series of this dense layer. So after merging, you can see this is a series of dense layer. So here we have this X is dense layer, then again input is X, then again X is equal to dense layer activate X and X. So these are the three. So it's like a deep densely connected network on top. So we have connected that, and then finally we add the main layer, which is the main output layer. So again this is a dense layer. Activation use is sigmoid, and the name of that is main output, and then it applies on the X, which is the final X here. This is that X. I am just marking it here. This is that X. So now you have this main output. Then you have to basically create the model object. So you now again, as shown in the previous video as part of intro to functional API. So here this is the model, and now we are providing inputs as the list. So one is the main input, another is the auxiliary input, and output is main output and auxiliary output. So that is what even we did there, where we considered it as just input tensor, output tensor. So same thing here, the input and then the output. Then you compile. So you compile the optimizer, use this RMS prop. Then loss we are going to measure for main output and auxiliary output as the binary cross entropy, and then the weights are used as 1 and here 0.2. So this is what compilation. Then you get the model summary. Then comes the data generation. So let me first do this part so that we don't have to spend too much time later. So let me just say import keras. So I'll just import keras. So then I will basically make use of this input embedding LSTM dense and then the model. So this is done. So we are basically having this main input. So this is that input layer. Then we are executing X. Then we got this, it is like an output of embedding layer. Then LSTM layer and LSTM output is provided basically. So this is auxiliary input, and then auxiliary output is LSTM out and the dense layer. Then we have this concatenation, that is the merging. Then these are the deep layers. Then the final output. Then you are going to compile. So it's going to compile. So I think I didn't do all the steps properly. So let me just once again do it. Yeah. So it's now compiling. So it has compiled. Now let me just take a look at summary. So this is the summary. So you can see this model is model whatever the name it has given, and then there is an input layer, then there is an embedding which we are given, then LSTM, then auxiliary input as input layer, then we have done concatenation, then dense, then the final output, and then the auxiliary output. So exactly this is what I have shown you as part of this slide. Okay, so this is that. Now we have to basically give the data. So that is the data is we are going to make use of numpy. So random seed is 0. Then we are creating the main data and the auxiliary data. So main data is the 1000 or the 10,000 the things that we are going to give, and this is like a time information. So here we are just going to create main data and auxiliary data. Then main output and auxiliary output, again we are making use of random.random. Then we are doing the fitment of the model. So this is here you can see there are two inputs. So input, main input, auxiliary input, and main output and auxiliary output. So this is the way you fit on the multi input multi output type of problem. So we have done the fitment. So it will take its own time basically. So I'm just running it for 2 epochs. So you can obviously run in when you actually do your own hands-on, then you can run here. So obviously the loss is very high, main output loss is 0.7 and all that, because we are using some random data, and you can very well see this is an NP random we are using. However, it is simulating, so we get it, and then using this we have this main input and then the auxiliary input. So we are going to do the prediction. So you can do the prediction and then you can get the data as per the basically whatever the main data and the auxiliary data. So this is the prediction. So this is what actually we have done or understood as part of this demonstration, like how multi-input, multi-output can be considered. Then we just simulated sort of feats by using, obviously we have used here the NP random or NP arrays, numpy arrays, and the random generation for auxiliary input, that is main input, as well as for the auxiliary input, and then we have created the model. Then we can see that this model is basically you can see this is like a graph. Main input, then embedding, you can see all that connected to, you can see this is a connection information here. So that is connected to this, then this is connected to this, is like a graph. So that's the way you basically understand or you work with multi-input, multi-output type of problems. You can apply it to you as per your now like your own understanding or your own other problems that you wish to solve. So I hope you like this video and this multi-input, multi-output, because in the previous one we have considered very basics of introduction to functional API, and in this we have gone little further and tried to understand about multi-input, multi-output type of approach. Thank you.
Hi, welcome to deep learning tutorial. For today's video we are going to cover convolution neural network. That's one of the very important topic with respect to neural network and deep learning. So we are going to understand that thing today, and we are not just going to stop at only understanding theoretically, but we are also going to use it we are going to do hands-on experiment with respect to convolution neural network. So let's get going. So the topics for today is CNN, then we'll understand what is convolution. When we say that it's a convolutional neural network, so we'll understand what is convolution, then we'll understand what is the CNN structure, and then we'll go towards using all the things that we just have learned, so that we can do the practical, or we can understand the practical aspects. So you should, I hope you are liking the videos, so you should subscribe to the channel, and then if in case you are liking videos, then please like those videos. Then apart from that, also share your comments, either in the comment section or you can email me. So let's get going now. So convolutional neural network. So first let's try to get into what is the need for convolutional neural network. So the need is basically, when we talk about doing image processing, computer vision type of applications, then convolution basically happens to be one of the important processing terminology, or one of the important processing aspect when we have to do image processing. So for example, when we have to do JPEG processing, when we have to do say MPEG processing, MPEG 2 or MPEG 4 or H.264 and stuff like that, then in all these cases typically convolution comes into picture, and convolution happens to be one of the very important aspect as far as the signal processing goes. Similarly, as part of computer vision, you need to do that. You need to have a way where you talk about identifying the different features and enhancing the features and stuff like that. So essentially, as part of image processing, computer vision, you require, or convolution happens to be one of the important aspects. Apart from that, there are several such things like transformations and all that. So as we proceed, as and when required, I will talk about it. So what is CNN? It is also called as ConvNet in terms of convolutional neural network. So it's a short form probably. So ConvNet. Okay. So essentially it's a deep learning algorithm. So what does it mean? You can actually take an input image, and then what do you do is that, because now we are talking about deep learning algorithm, so you assign importance, or that is basically the weights, and that you now know that the weights are basically the thing which are controlling the behavior, or behavior of the layers. Okay, so you basically assign importance or learnable weights, oblique biases, to various aspects or objects in the image. That means now you are actually, because that job will be done by layer. So having said that the job is basically done by layer, you have to obviously you know that suppose if there is an image, then the way in which we take camera, say for example we take we use camera of a mobile phone, then it tries to basically focus on the face rather than on your chest, or say stomach or some such area. Typically it tries to figure out whether the head is stable, where are the eyes and stuff like that. So basically it's trying to give the importance. Okay, so on the similar lines these algorithms work. Okay, so it's a deep learning algorithm. Then how does it help me? So it can help you to decide, or it can help you to differentiate amongst the images from one another. That means suppose if you have say group of images and you want to tag it, and then in that case, suppose if you have a group of images of say human beings, then another group is of say, let's say say birds, another group is of let's say animals, then you probably can run such algorithm, and which will try to decipher, or which will try to differentiate images from one another. Okay, so the another example could be, you have say horse and say dog, then the variety of horses are there, variety of dogs are there, and then you basically have a lot of images of that, and then you want to differentiate. So some such these are some of those examples where practical examples where ConvNet is used. Okay, so another aspect that comes is spatial and temporal. Okay, so that's very important. And why this is important is because when we talk about an image,
And when we talk about a moving image, these are the two different aspects. So that means when we are talking about a video, which is essentially a you are trying to capture a frame by frame. So there are two aspects to it. One is a spatial and another is a temporal. So within a particular image, that particular aspect is called as spatial aspect of an image, and another is basically within the different slices or within the different frames that you have as part of taking say video recording, then you are going to basically get frames. So in that case you have temporal dependency. That means it's essentially it's a time wise dependencies are there. Without going into too much of detail, essentially it's like within a particular image it is called as spatial dependency, and across the images, that means when you do video recording, then in that case there is a temporal dependency, and both can be tackled by using convolutional neural network. Okay, and that's why it plays a very important role when we talk about doing image processing or and computer vision and stuff like that. So let's get into convolution now. So let's say I have an image on the screen. I have shown you that it is an image of size say 6 pixels by 6 pixel. Okay, so that's what I have written it here. So it's a 6 pixel by 6 pixel, and then you can see that these 3 by 3 block is shown in blue numbers, and the rest is in black numbers. Okay, now I want to basically carry out a convolution. That means what? So basically I am going to do some sort of multiplication. So convolution is a very standard terminology of signal processing systems, and normally students tend to learn it as part of signals and systems or digital signal processing, and then obviously in image processing. So all these are the places where normally a student is expected to learn or understand convolution. Okay. So now basically I want to do some sort of multiplication, and there is a sort of shifting that we will apply to multiplication. So let's understand it now. So now let's say I have another mask, it is called as, and there I have written 0 1 1 0 1 0 1 0 1 like that. It's a 3 by 3 mask. So it's my responsibility or it is my duty to create the mask. So that is where the as part of image processing, whatever suits or whatever is required, I can basically have my own mask. Okay, so I can create a mask. So that means now I want to multiply or I want to superimpose this mask on the 3 by 3 pixel area of the 6 by 6 image. That means you have this image as a 6 by 6 image, and on this I am going to superimpose. However, when I do superimposing, it's not just putting it on it, but essentially you are actually trying to do the multiplication. Okay, that's why 0 1 0 1 is written. So if I just do this 3 by 3 multiplication, so essentially it becomes like a matrix multiplication. So you are going to get like 1 1 1 multiplied by 0, then 2 2 2 multiplied by 1, and then 163 multiplied by 0. So this is the first column that we have taken. Then we are adding 225 into 1, then 32 into 0, and then 110 into 1. So this is that, and then 41 multiplied by 0, then 92 multiplied by 1, and 184 multiplied by 0. Okay, so I get the total as 649. Okay, so that means this particular block, which is of 6 by 6 image, and in that I have chosen 3 by 3. So I started from this block, and when I used a mask of such a mask which is my prerogative or which is my decision which mask I want to take, so I get a number 649. So in a way what I am doing is basically I have actually reduced the size of that particular source image. Okay, so what does it mean is, so if I just use a 6 by 6 image and to it I multiply by using say 3 by 3 mask, then I am going to get 4 by 4. Why? Because that will become clear. So let's see now. So I am trying to put here 649. Similarly, if I use a 5 by 5 mask, then in that case I will get a 2 by 2 image. That means 6 by 6 image, on I am multiplying it with a 5 by 5 mask, and I am going to get 2 by 2 image. Okay, so let's now concentrate on 3 by 3 image, and we are now going to shift this mask. Okay, So now we have shifted it by one on the row wise. Basically you can rather on the column wise we have shifted by one, not the row wise in this diagram. So here basically you can see that now it is the numbers are in sort of in between. Okay, so 111 and then 222 163 230. So this is the blue 3 by 3. Now I am once again applying the same mask. The mask remains the same, and now I am once again going to get a value doing the same matrix multiplication, and I am going to get 594. So now basically I'll form such a image which is of 4 by 4 size, and that means from a 6 by 6 image I have reduced, or I have come up, I have basically came to image of size 6 by 4 by 4 using a mask of 3 by 3, and I shift, so I continue the process, and that way I can fill the dashes that are marked here. Okay, so that's essentially the process of convolution. Okay, now as part of image processing, people basically make use of it very intelligently, so that basically as part of those algorithms people use different transforms are there. So like we normally students study Fourier transform, so there is something like cosine transform and all that. So typically these are the examples or these are the practical usages of the transforms as part of image processing. So will not go into too much of detail, but essentially from 6 by 6 I have come down to a 4 by 4 image. So now we have to concentrate, or we have to understand the second point, that is about the CNN structure. Okay, so what is the CNN structure? So let's now understand it. This is a very standard diagram that normally you will find. So you basically have tried to give an input, and then from input you are trying to identify whether the input is a particular vehicle, so whether is it a car or whether it is a truck or a van or a bicycle or whatever. Okay, so that means it is going to pass through these many things. So something, that process is actually, or that part is called as feature learning, and then the second part is basically where you actually take a decision or you classify. Okay, so what is the basic structure of CNN? So CNN is basically the structure is you initially perform the convolution, then there is a ReLU that is shown in this diagram. So we will, anyway I have told you about all those activation functions earlier. So normally ReLU is a very commonly used function. I have told you that it's a very widely used function. So we'll anyway use this as when we do hands-on. Then you do pooling. So what is pooling? I'll explain you shortly. Then we once again do convolution, and once again we do pooling. Then we give it to a fully connected network, because that's where actually you are going to do some decision making, and that's why there is a softmax layer which helps me to decide on different classes. So classes means like whether it is a car or whether it is a truck or a van or whatever. Okay, so and then that's why you have this fully connected layer, and then you finally get the output. Okay, so let's now go into these aspects. So convolution is the act of taking the original data, creating the feature maps from it. So I told you basically what the convolution process, so and how we created the important aspects, or we kept on shifting it using the feature that I am interested in, or using the mask that I am interested in, which will allow me to concentrate on a particular feature. Okay, then the second point comes as a pooling. So what is pooling? Pooling is relatively easy to understand. It's like a downsampling. Okay, so I want to reduce the size of image further down. It's not convolution, so basically it's a simple technique. So I'm going to downsample the things. That means I want to still reduce the size. Why all these things are done in in all this convolutional neural network, or for that matter image and video processing? Because if you want to process the real input, the complete input, then it requires good amount of memory as well as processing power, because your image sizes could be like suppose if you tend to take a high definition HD camera, or even VGA or more than VGA, then still the processing amount of processing and memory requires is huge. That's why people use all these techniques, so that you actually work on a smaller size and you don't work on the full this one. Okay, the full size. Okay, so normally people make use of a concept, or the approach called as max pooling. Okay, so max pooling, what do you do? So basically you select a region, and in that region you find out a maximum value, and then that maximum happens to be representative of the entire region. Okay, So probably here people use the transformations like constant transforms and all that. Okay, so that can be one of the approach. It's not that it has to be like that, but there can be even that can be considered. Okay, anyway, so other pooling approaches, average pooling, where people tend to take a average. So how does it look? If I want to put it in a very simple way, so now you have, say for example, in blue, green, yellow and red, you have these four inputs, 2 by 2 say, and now I am going to do max pooling. So from that blue region I am going to pull 9 because it's a maximum value, that means it is representative of that area. Then 7 happens to be the another representative for green, similarly 8 for yeah, average, 8 for yellow, and then 6 for the red one. Okay, the other approach can be you take an average of, instead of pulling out only maximum, you have to take average, and then that becomes the representative. However, people most of the time use max pooling because average means you have to once again do some more operations, and they don't want to keep on consuming CPU cycles for doing such operations. So they tend to use max pooling, which happens to be relatively simpler approach. Then let's quickly understand the FC layer or a fully connected layer. So fully connected layers typically is part of the decision making process, which is obviously it's a dense layer. So all nodes are fully connected, and typically it is used for a way of learning non-linear combinations, because now you are going to get non-linear combinations of high level features. That means which is going to be the output of convolutional layer. Okay, because the convolution thing will be performed as part of convolution layer, and then you are going to get lot of data or lot of so you have to basically do learning of non-linear combination. Okay, so FC layer is learning a possibly non-linear function. FC layer is learning a possibly non-linear function in that space. So that's the way literature puts it. Okay, so you basically are going to make use of fully connected or a dense layer as part of the fully connected layer. Okay, and it's going to perform the non-linear learning non-linear combinations of the high level feature. So that's basically about the key aspects of convolutional neural network, where we understood the convolution, then we understood the pooling, and then the dense layer or a fully connected layer as part of the output layer. Okay, output of the convolution layer. Okay. Now let's get into what is the support to me in Keras, because now I have told you ये करना है वो करना है, तो मुझे मेरे लिए support क्या है Keras में. So Keras actually has a functionality which is called as con2D, because we are talking about a 2D data. So there are, it takes it's a function call, and it takes a lot of parameters. So I have given written here only the mandated or a compulsory parameter. So compulsory parameters are like filters, then the kernel size, and then the input shape is also important. So filters and kernel size, basically these are the mandatory parameter. So filter is what? Essentially it's a number of filters that convolution layers will learn from. Okay, so it is basically determining the number of output filters in the convolution. Okay, because I have told you like one mask or a filter that was there, so it is basically going to decide how many such filters I am going to use. So normally these values will be 32 or 64. We'll use either of that. Okay, so in hands-on experiment we will be using this. Then the kernel size, so it determines the dimension of the kernel. So you can have a 3 by 3 kernel or a 5 by 5 or 7 by 7 like this. So typically it's an odd number, this one. So the filter that we have chosen basically was 3 by 3. So that is what basically this corresponds to kernel size. Then the input shape is the shape of input image, because we have to inform the input layer what is the shape of the input image. Because if my image is, let's say, of size 800 by 600, obviously I am not going to give full 800 by 600. I probably have to give some shape like say 8 by 8 or say 50 by 50 or some such thing. Okay, and then using that I basically completely cover the full image. Okay, because I cannot do full image in one chunk. I cannot work on full such a big size image of say 1000 by 768 or 1323 by whatever. Okay, so HD size 1920 by 1080 and all that. It cannot be just done in one go. So I do handle it in batches. So obviously we'll have to work on the shape. Then comes the activation. So this I have explained you before in my previous video. So those who didn't go through that, you can take a look at it. So activation functions, basically it's a function called activation, and there you define
which activation you want to make use. So there is a relu, sigmoid, softmax, like that we have seen previously. Okay. Then pooling. So pooling is basically you have to define, it's a max pooling 2D, it's a function call by name max pooling 2D, and in that the parameter that we need to define is pool size, because we have to handle it like basically you are downsampling it by 2 here on both row size as well as in the row wise as well as column wise. So here pool size will be, pool underscore size will be 2 by 2. Okay. So now as part of doing hands-on, we are going to classify images of say dogs and cat. That's a very huge database that is available, almost 1 gigabytes of data. So that database is available, that database of images is available on Microsoft.com. So those ID is given here. Then we are going to make use of OpenCV library, which is basically image processing library. Then we are also going to generate data, because the data is of huge data which is of dogs and cats, so it's difficult to use directly. You have to do some, you have to work on generating the data for training as well as for testing. Then I am also going to tell you something additional. This is not mandatory, but it helps because the data being huge, people normally don't keep on doing the things everything same thing, because they will train the model and then they will save it. Okay, so that is where the important job comes, that is save and retrieve model. However, this is not a mandatory step, but it is used in practice, because virtually it is impossible to keep on doing the same training and thing every time, because it may not even help you, because answers might differ and stuff like that. Okay, so save and retrieve the model is an important step. That way, when it comes to doing using it practically, then we are going to perform the convolutional neural network. In that, we are going to basically add layers, and then we are going to define activation, pooling. Similarly, activation, pooling. Then we are going to do flattening. I explained you this in my previous video, how we do flattening and why it is required. And we are going to make use of dense layer as part of the decision making, and then obviously we are going to add a output layer. So that means it's going to be now a multi-layer solution as part of doing the classification of images. Then we are going to do compilation, then we are going to do fitment, and then basically we can actually after doing fitment we can use it to predict, or you can use it to evaluate. Okay, so that's basically the thing about convolutional neural network. So in this video we have seen what is convolution, then we have gone through the concepts like pooling, then the other things like basically the activation functions that we already know, and then we are going to do this hands-on experiment, that is classifying the images. So I hope you like this video. So please subscribe to this channel, and subscribe to my channel, and also email the comments or doubts to smltech16@gmail.com. So in the next video, I'll be actually showing you this experiment, which I have shown it as hands-on. So we'll be performing this experiment hands-on. Thank you. Hi everyone, welcome to Deep Learning tutorial series. My name is Srirang Korde. I think I have done a lot of videos up to now. Now for today's video, we are going to basically do hands-on programming for convolutional neural network. Okay. So this is the same thing that I have told you in my previous video. So those people who didn't see the previous video can take a look at it to understand the different concepts about convolution and the other related things. So as part of doing this hands-on experiment, we are going to classify the images of dogs and cat. This image set, or these data set is available at Microsoft.com, and this is the URL that is mentioned. For doing this experiment, we are going to make use of OpenCV library, which is basically an image processing library. Then we are going to generate data for training and testing. Then we are going to save and retrieve the model. Now this is a very common practice that is done in reality, because first of all the data sets are going to be huge. So every time you cannot keep on downloading the data, or probably you cannot keep on training the data. That's why whatever the data that you have generated, that will be saved. Okay, and then you retrieve that data.
Similarly, you that means that's part of the model. Okay, so save and retrieve the model. Then you do the actual job, that is perform the convolutional aspect. So that is, you are going to add the CNN layer, you are going to add activation, then pooling, then one more layer, then you are going to do flattening, and then you are going to have the output layer. Okay, and then you are compiling, and then you are fitting. So that's basically the thing that you are going to do. So before we proceed to the Jupyter notebook, just would like to remind you, please try to subscribe to the channel, and then if you have any doubts, please write an email, or you can like the videos, and then also can put the comments in the video box. So now we'll go and understand this implementation. Okay. So in this implementation, as I told you in the example, that we are going to basically classify the images. So for that we are going to require numpy, then we are going to basically require matplotlib. So, and then another module that we require is, basically we are going to use the OS module, that is part of Python. Okay, so we are going to use Python OS. Then apart from that, there is a prerequisite of OpenCV, which is basically image processing library. So for installing, you require you have to do pip install OpenCV. So if you can do pip install OpenCV, then for you are done. Then after that, once it is installed, you can actually uh, import it. Okay, so let me just quickly magnify it. So little bit magnification. So now you have this importing of the CV library. I presume that the CV OpenCV is installed, which is a OpenCV Python library. So you have to import it by saying import CV2. Okay, that you have to understand. Then I have downloaded the data set in the folder, whatever you can see it here, Python whatever data projects, pet images. Okay, and then I know that in this images there are two categories of images are there. One is dog and another is a cat. Okay, now there are close to 25,000 images are there, and the data set is close to almost 1 GB in size. So there are half are dog images and half are cat images. Okay, so we want, what are we going to do is, initially we are just going to take one picture or 166th index of dog. There is no reason that I have chosen 66. We can choose anything from, say, almost close to 12,500 odd images are available. So you can choose anything whichever you feel like, but I just chose some random number. Okay, so now you got this image, and then you want to basically read this image. So to reading this image, you are going to make use of CV library, that is OpenCV library, and you basically are going to read only grayscale. It's essentially, it's a colored image, but for doing image processing, it becomes otherwise difficult if you take care of the color and all that, because processing increases. Here itself will find processing itself is pretty heavy. So but as part of few other videos, I will tell you how to handle it with keras and all the colors and all that can be also handled. But for today's for this video, we are not going to do that. Okay, so there is a way to do that. That's not that we cannot handle, rather we will be handling colored image, but not for today. Okay, rather we are, this is a colored image, but we are only concentrating on the black and white sort of this one. So that is one information, which is Y information. Then we will show the image. So since it's a grayscale image, I'm reading it like a grayscale, so I'll show the image. Okay, and then let me just run this. So then I have taken the file, so you can see it has taken the file. Then I am going to take the image. Okay, I have not imported, I think, few things, so let me just import. Yeah, so you can now see that image of 66 dog is like this. So if you change it, then you can basically see it. So suppose if I just change it here to say 67, then it does some other this one can come. So suppose if I just do it, say 69 probably. So let me just run this, then I can read this, and you can see this some different dog. Okay, so for the time being, we'll keep it as it is, whatever I have kept it as 66. Okay, right. Now we can see we can print the data. So obviously it's going to be a data of grayscale data. It's because we have taken only the basically image has three components: RGB. There is another representation of RGB is actually YCBCR, or it is also referred as YUV. So Y corresponds to luminance. Okay, so we are going to make use of those values. Okay, so Y is the dominant value, so we are going to use that. So you can see this image has some values. Okay, now these values are basically between 0 to 255. Then we can also take the shape of the image. So you can get the shape of the image. So image is of size 397 by 500. Now in this data set, the images are of varied size. Okay, that's why we have to make it uniform, and we don't want to work on such a big size image because it's relatively a bigger size image. Otherwise the processing takes good amount of time. So what we do is we resize it and we make the image as 50 by 50. That's why the main purpose of using CB here is to it's simple to use, and then we are also going to use it for doing resizing. So the image size, instead of 397 by 500, it will become 50 by 50. Okay, so I can just run it and you can see the 50 by 50 looks like this. Okay, so there is a change now. You can see this was the grayscale image, now it just looks like little different. Obviously the it's not very good quality. The quality has deteriorated because I have made it 50 by 50 instead of the size 397 by 500. Okay, then I have made it gray here, that's why, otherwise it would have come something like this. Okay, because here I didn't do gray. Okay, anyway, so now there is a function that we require to write, and that is called as a training data. So we have to create a training data. Now this training data function is basically what it is doing. So there are this, let me go back and explain you this. So one is a data directory, another is a category. So I have created an array with two entries. So index 0 is a dog and index 1 is cat. So I am going to parse the data and create a and write a category. So first category is of dog, and that is 0th index, and the first index is a cat. That means another category is a cat. Okay, so that's what basically this particular thing is. Okay, so what are we going to do? So for each category, because we want to basically divide and give a label. Okay, give a number, basically 0 and 1, because it doesn't have number, so it has only images. So we want to add one more column to it, that means classifying that whether if it is a dog image, then it will be dog, if it is a cat, then it will be cat. Okay, so we are just iterating on categories, and then we are taking the data directory, and then we are basically using the index of category, and then we are basically taking the path which is of the image. So os.list directory, and it gives me the full path, which is the data directory and then the category. So dog has its own images, similarly cat has its own images. So we can I can quickly show you this so that it becomes clear how this looks. So suppose if I open my this one, and if I go here, you can see this is the cat and dog, and in the cat there are so many images of cat. Similarly dog, it has so many images of dog. Okay, so that's basically the folder cat and dog. Okay, so let's go to our code. So now we are written this function which will basically put it rather which will basically classify it, and then it will form an array. So that is very important. And so array is like you read the original image in the grayscale format, and then you, in the new array, you basically resize it because there are so many in number. So this can be done in a very quick another way in Keras, but that is a little difficult or tedious way, and for first lecture, rather on the first initial level at the CNN, that may be difficult to understand it. That's why we are using CV2. So CVT will help me to resize. So now you can see I am forming another array, and then the actual training data has two columns or two information. One is a new array, and the another is a class num which I am forming it here. So it will have either 0 or 1 depending on whether it is a cat or a dog. Okay, so that's the function. So I invoke this function, and now this function takes good amount of time. Okay, so that's the reason I will not invoke it now. because it will take almost more than 5 minutes to 10 minutes it will take, because images are large in number. Okay, so so now what I will do is, another thing is that even if I run in front of you, probably you can get a feel of it, but it is going to take good amount of time. So you can see that it is started running and it will take good amount of time. So then basically will have to get the length of the training data. So now what I will do is, I will basically explain you this complete program, and hopefully by the time this would have run, otherwise I will put it in another video about, I'll once again start from this place. Okay, so let's see. So you will get a link. So anyway, you can't run it now because it is this particular process is running, or this particular task is running. Now we will be importing the random, and then you basically are going to shuffle the data. Okay, why you are going to do the shuffling of the data? Because you don't want the way in which it is in the order. Okay, so that you can do, and after that you can actually print the sample. So some sample data of say 0 to 10 you can do. Then you want to form the two arrays. So one is a feature array and another is a label. So label is just 0 and 1, which is cat and dog or cat, whatever. Yeah, so index dog and cat, and this is actually the x is a feature. Okay, that's the terminology that we use in deep learning. Okay, so we can actually append it. So you can see now x will have all the features, that means all the images, and then y will have the corresponding label to it. Okay, then I can convert it into the numpy array. Then I can reshape it, because I want to reshape it so that it becomes a 1D array, and then I can do it for all the features. So there are basically, and then it's a grayscale, so I have passed it from -1, so it's a numpy functionality I am using, and then I can print a few this one. Now what will I do by the time, because this is I believe still running, so what I can do is, I can make use of the model that I have already saved. Okay, that because then only we'll be able to proceed, otherwise we have to wait. Okay, so we can save that. So whatever the model after this task, that means training data getting generated, then numpy stuff, then creating features and labels and all that. Okay, reshaping and all that. So then you basically can make use of this information, and this particular information is saved in a pickle model. So this is not the neural network model, but essentially it's like a pickle. Okay, so pickle is a library. So for that we have imported pickle, then you open this x.pickle, similarly open y.pickle. Now we are not basically going to save it, because this process is still running. Okay, so you can see the star is there, that means it is running, it takes good amount of time. So what will I do? I will retrieve the model, because I have already saved it before starting this video recording. So basically I will just retrieve this. So if I run it, now again this will not run, because the upper task is yet to get over. Okay, but however I will just explain this. So you can import, and then it will load x and it will load the y values. So now I will stop for this video. I'll stop for this video, and then I'll come back basically after a few minutes, once this execution gets over. Thank you. Hi everyone. So let's continue where we have stopped in the previous video about doing hands-on about convolutional neural network. So we'll just this basically got completed just now. So I'll just run this in front of you. So you can see that it has close to 25,000 pictures. That is the length of the data. Okay, so we have created the training data. Then I was telling you that we can use import random, and then we can shuffle the data. Okay, because all those close to 25,000 pictures will be shuffled. Okay, and then the 0 is for the dog and the 1 is for the cat. Okay, so that's what. So sample 0. So here you can see we are iterating for say 10 pictures. Okay, so it will basically, when we do that, so 0th is actual image data, so it will be now 0 to 255 value. So we are not interested right now, we are interested in only 0 or 1, so that we know whether is it a dog or a cat. Okay, so we can just run this program. So you can see 1 1 1 whatever. Okay, so it's like dog cat, these are all jumbled up. Okay, because we have shuffled it, otherwise it would have been in sequence. Okay, so we don't want it like that. Okay, so we want data which will be shuffled up. Okay, so that's the reason we have executed, and then once again if I run it, so it will be little different. Now you can see it is once again changed. Okay, so like that. Okay, so that depends on how you basically are doing this random shuffling. Now you can see once again it got changed. Okay, then we are going to form the features. Okay, that is feature array and the label array. Okay, so x will be for feature and y is for the label. लेबल मतलब जो डॉग है या कैट है वो लेबल है, ठीक है, और जो फीचर्स है मतलब जो बेसिकली डेटा जो है उसको हम लोग प्रोसेस करने वाले हैं. ओके, सो ट्रेनिंग डेटा इज बेसिकली न्यू अरे जो हमने वो ऊपर में क्रिएट किया था, दैट इज एक्चुअली इमेज डेटा और उसके लेबल से. ठीक है, so ये अब हम लोग इसको we'll just execute it. So we'll get this sorry, I didn't run this. So once I run this, then I'll basically get x and y. Then I will have to convert it, because now this is no more this is not this is just a Python array, so I want to convert it to NumPy array. So I'll convert into NumPy array because that's what we use it as part of processing. We require NumPy array. So we have done this. Now we will reshape it. So now it is, you can see basically these values are some 5 values I have printed of the this one. So you can see this is the first group, second group, like the third, fourth and fifth. Okay, so these are the 5 values I have printed. Now I want to basically reshape it so that it becomes a uniform array. Okay, so I'll reshape it because now it is a NumPy array, so I can use the reshape functionality. And now here the reshaping is of 50 by 50 images. So basically this is a 50 by 50 image size that we now know. Okay, image size was defined as 50. So for all this one, that is minus for all the features, that is size, and then we are talking about the grayscale image. So we'll reshape it and then we'll print it. Okay, so now you can see the format has changed. It's now like a one single array. Okay, so now there's a huge, it will be printed shown like this. Okay, so then we can save the model. So whatever the model that we have created just now, so that we can save. I don't want to right now save it because saving also will take a little bit of time, no, but that's okay. You can always save it, and the saving is very easy. You just take care of pickle and then you open x.pickle, that is the name of the file, then you say dump, and then similarly when you want to save y, you similarly say for y. And if I want to retrieve, so you will just open the name of the file and then you say load instead of dump. Now you have to do loading for x as well as for y. So I'm going to, without saving, I'm going to load this because I don't want to just, this was done previously, so this will help you quickly understand it rather than once again taking some time. Okay, so I'll just run this, then I will basically load this, and then I will perform the convolutional neural network processing now. So for that I require keras, so I will import it, which is basically, it will import the TensorFlow. So it has basically imported. Then you require different models. So we are going to use sequential model. Rather, we require only one model, but we are going to require multiple other things from layers. So layers, we are going to use dense, activation, flattening, then con 2D, and then the max pooling. So pooling I have explained you earlier. Okay, and this also functionality was explained to you in the previous videos. Now we are going to normalize the data because I told you the value is from 0 to 255 and we want it to be between 0 to 1. Okay, so we'll normalize that. Now you can see the shape. Now you can see the shape is still 25,000. 25,000 pictures are there and each of size 50 by 50, and basically it is the y values or the important grayscale values. Okay, so that's what. Now I want basically to give it to the model, and now to the model what I have to give the shape. Okay, now that's what I told you as part of previous video, that we require shape to be given. So which shape? So we want 50 by 50 images and only of gray values. Okay, so that means it's not 3 but it's only 1. Otherwise if it is YCBCR or YUV, then it will be 3 different things. So we are not going into it right now. We are using only grayscale images, grayscale part of the image, colored image. Okay, so we are basically so x shape 1 colon will give me this. Okay, so if I run it, so we are going to get 1 colon, that means 50 by 50 I am going to give the values. Okay, so now we will define the model. So first model is the model is equal to sequential, so that I have told you it's very widely used model. उसके बाद we are going to add a layer. So in this layer we are going to have the first layer, where we are using this con 2D, that is convolution 2D. This is the 64, which is the filter value. Then 3 by 3 is the mask that I have explained you, and the shape you can see this is the x dot shape 1 colon. So same thing, 50 51. So this is what filters, and 3 by 3 is the kernel size. It is also called as kernel size. Okay. Then we have added the activation, which is ReLU. Okay. Then we have added the max pooling done, so which is a 2 by 2 windows, 2 by 2 window size, so pool size. So let me just run this in front of you. So you can see this has run. Similarly, there is another layer which is 3 by 3. So output of this portion is 3 by 3. Okay, that's basically okay. So this is that 3 by 3. It will be in that pieces of 3 by 3. So we have used the layer 2, which is 3 by 3. Then here activation is ReLU, and then pool size is 2 by 2. So this is the second layer of the neural network. Then the third layer is we are going to flatten it, and we are going to add a dense layer. So we will first flatten it, then we are going to add the dense layer. So this was explained to you previously. Let me just go back. So this was that diagram. You can see this. So this is the feature learning, and this is the flattening and fully connected. Okay, so this was that portion. So flattening and then the dense layer. Okay, so that is what layer 3 we are done, and then the final layer, that is the output layer. There is only one neuron, there is one, and then the activation is sigmoid. We are using sigmoid because we want to do binary classification. That means either is it a dog or whether it is a cat. Okay. Then we are going to do compilation of the model. So these steps were explained to you in the previous video, previous to previous probably, but we have gone through all this. So we have defined the loss function as cross entropy binary, because it's a two thing, that is dog or a cat. So then optimizer is Adam, which is the gradient descent, and the metrics is we are going to measure the accuracy. So let me just run the second layer. Let me just run the first layer, then second layer, then third. By the way, you can also run this line by shift enter. Okay, so shift enter also can help you. Now we'll see the model summary. So you can see we have used 48 by 48 because the entry was 50. So the two are, it will leave it as their internal thing, that is something called as stride. Okay, so we'll not go into those technicalities right now. So basically it is going to take 48 and 48, and then 64 was the size that we are given. Then activation again remains the same. Then the second layer, you can see this is the pooling. So it has become, after pooling, so it was like a downsampling by 2, so it has become 24. And similarly this will become now 50 has become 48. So similarly this will become 20. This will remain, this particular thing now will remain 22, and then max pooling will make it half, that is 11. Then flattening, so this is that number, then dense, and then the final one was taking 1. Okay, and then the activation again 1. Okay, so this is what the model summary. So then we are going to do the training. So now this is very interesting. When we want to do training, we have to make use of some functionality called as train test split. So that means of the 25,000, it is going to split the data into two parts. So one part will be training, for it will be used for training. So wherever train is used, so this is for training, and this is for use for testing. So test is for testing, x test and y test is the testing. That means we'll train it on the we will train it on the some portion of training data, and the remaining portion of the training data will be used for testing. So you can see x is given here and y is given. So यहाँ पे हमने test size is equal to 0.3 लिया या 0.2 लिया, जो भी, we can change it like this. So for the time being, let me make it here 0.2. That means 20% will be testing portion, x test, and remaining 80% will be for training, okay, of this x and y. So I just, you can say it will take time. Okay, so it is currently marked star. Then after that we have to do fitment. So currently I am just going to do fitment for epochs 1, because even to run one epoch it takes significant amount of time. Okay, so I'll just run this in front of you. You can see it is basically, it will start now, and it will take a good amount of time. So you can see it is telling me almost, yeah, so almost good a few minutes it will take to complete. Okay, so for the time being I will stop my recording and we will continue from here. Okay, so we will now continue where we have stopped. So you can now see that it has completed just one epoch, and it has taken basically given accuracy of 0.7033. Okay, so that is the accuracy. Now if you increase the epoch to say 20 or say 50 like that, then obviously your accuracy will increase. Now this particular thing is not just depends on epoch, but it also depends on trend test split and also the shuffling that we have done. So for example, if I just once again run trend test split, and if I change this ratio, or because trend test split also puts randomness, because it will take some random 80% sample in training and remaining 20 in test. Okay, so that is also that will also change. So depending on that, there is a chance that you may get a lower accuracy or you may get a higher accuracy. That depends on even this one. That's why the reason is people don't keep on changing once the model is trained and it gives a sufficient good accuracy. That's why that pickle concept is there, or pickle usage of pickle is there, where they tend to use. Okay, so here you can say it is accuracy is okay as far as first epoch goes. Obviously if you run it more, it will keep on improving. Okay, so you can for running one itself it has taken decent amount of time. Okay, so now we will go and run this predict. So we will now see what we will do is we will now, so now our model is ready. Okay, because now we have done the fitment, so we can do the predict. So we can now we are, you can see I am using testing. So we'll just do this, and it will take some time to do the prediction. So it's taking time to do the prediction. Yeah, so it has done the prediction. Now we can check some, say for example 0th YP. Okay, because again test was having remaining of the that means train was having 80%, and the remaining 20% of those 25,000 were with the test. Okay, so we are just trying to take the first, say for example 0th one. So you can see this is basically is an array of with the value 0.91. Okay, and now we'll try to see the shape. So obviously it's a only one value. Okay, now really what was the actual this one? So y test is actually the truth. Okay, so we'll now see. So it is 1. So now you can see it is very closer to 0.91, is very closer. That's why you require a that's why you used here the layer that was done here as part of activation. So in the last layer you can see we have made use of this sigmoid. Okay, so since that means it is more than 0.5, it will go towards 1. Okay, and that is what we wanted. Okay, so now you can see 0.9 is very high value, so 0.91 is very close to 1. That's why it is going to give me the label as 1. That means it is a cat. Okay, and similarly this has also predicted cat. So it's a very pretty good accuracy even in the one run. Okay, but however I told you it is not always that you are going to get good accuracy. There is a chance that the accuracy could be close to 50% to 60% like that. So you can see basically, so this is there. Then you can also use evaluate and see how the basically for all the x test and y test how it is performing. Okay, so that means internally this evaluate calculates the predicted value, the way in which I have done it for only one this one here, that is yp0 I shown you. It is going to do internally, and then it is going to do the prediction or evaluation. Okay, so here it will take and it will run it for say roughly 54990, and you will get the answer. So now it is almost nearing the completion. Yeah, so the answer is it is very high. So it is again, you can see that it is 0.74% or 0.74 is the accuracy. So this is about the overall usage of uh, convolutional neural network. So in this we basically have downloaded, or we have used the dog and cat, and then we wanted to classify whether the image. So for that we basically have uh, created a model, created the data first, that is the training data. Then we use that, then we basically can save it also. So that's what I told you, save the model, saving and retrieving. then you perform the convolutional neural network processing. So for that you make use of keras. Then you identify, then you basically define the sequential model, then you basically add those layers, layer 1, layer 2, then layer 3, and then the output layer. Then you do the compilation, then you basically do the fitment. Before and after that you split the information or split the training data into two parts, that is train part and the test part. Then you use fitment, so it will get trained, and then you test it using the test data. That is what evaluation will be there. So this completes our hands-on experience or hands-on activity with respect to the convolutional neural network. So subscribe. Thank you to for this watching this video. I hope you will enjoy this. Subscribe to the channel, and if you have comments, please send it to smltech16@gmail.com. Thank you. Hi everyone. As part of deep learning, we are basically going to cover a very important topic, that is the mathematics related to the gradient descent and the backpropagation. So in the previous videos, overall we have seen the usage of gradient descent, and then we have basically gone into the other aspects of deep learning, and obviously we have applied those to various situations. So now in this video we will try to first get a quick overview of gradient descent, and then we will get into the details about the gradients, and then we'll go into the backpropagation, and all these things are basically related to the mathematics or the maths that is overall related to these concepts. So in this video we will basically first take a look at gradient descent as an overview, then differentiation, partial differentiation, and then comes the gradients and the backpropagation. So let us try to understand the very basic linear algebra that we have seen in our school days. So like if I have given an equation y is equal to mx plus b, and suppose if let's say you know the values of m and b, or it is given to you, then we can put it as y is equal to say 2x plus 3. So now suppose if I, instead of that, whether if I know the values of m or b, now suppose if somebody has given me the values of x as, say for example, the square foot area of say apartments. So let's say these are the values of square feet, values of the apartment, which is the input, and then let us say these are the prices for those areas. Then we want to derive a prediction function which can help in predicting the future values, or say for that matter the different values. So there can be now multiple lines which can pass through these points. So how do I know which is the best point? So what I am trying to basically say, if I try to plot this x and y, then I am going to get such graph. So such points are there, say for example, say for 2500 say value is something like that. So you are going to get that graph. However, the line which is there can be multiple such lines. So now how do you know that which is the best fit line? Because then that particular line can be used to predict say the intermediate values or the future values, either way. Like suppose if you know the value of say the cost of say 3800 and 3200, then how do you come up with a value for say 4000 square feet apartment? So something like that, or for that matter say 5000 square feet apartment, and then what will be the value, what will be the price for that. So point here is, suppose if such is the data that is given, then you can always draw multiple lines, and which can pass through some points or it can pass through various points. So how do you know which is the best fit line? So for that basically people normally tend to use something called as mean squared error. So what will they do is, from those lines they will try to compute the delta, and then they will try to square up, and they will try to sum up and then divide by the number of points that are used in the calculation. So you collect all the deltas, then you square it, and then you sum and divide by the number of points. So that is what typically they will try to use as a mean square error to find the best fit line. This is one of the approach. So that means if I use this mean squared approach, then mean square error essentially will be 1 upon n, because we are dividing it by the number of points, and then summation of yi minus y predicted. Now yi is actually the truth or the observed value, rather yi is the truth, and then the y predicted is the predicted value, or which basically you are going to say that this is the predicted value. So that means it's like yi minus y predicted is actually the difference between the truth and the predicted. So yi is essentially the truth. So MAC is now basically 1 upon n, and then you are just trying to predict the value. So using again the mxi plus b. So MAC is now here, it is also called as cost function. So now we will shift to gradient descent as an algorithm. So what is it going to do for me? So it is going to find a best fit line for a given training data set. So the x values that are shown, that were shown previously, so basically they are going to be the training data. So this algorithm is basically an optimization algorithm which will be used to find the values of parameters. And what are those parameters? So parameters are basically the coefficients of a function that minimizes the cost function or the cost. So now this situation is similar the way in which we were trying to think of minimizing the loss and then propagating that and using the back propagation algorithm when we talk about the deep learning. That's why this approach is currently explained in this video. So the gradient descent is best when the parameters cannot be calculated analytically. That means we are not going to use linear algebra, and we need to do some sort of searching by an optimization algorithm. And that's where the gradient descent algorithm comes into picture. So we can try to imagine something like this. Suppose if I have a ball, so I will start with a random position on the surface, and from the random position on the surface I need to go to the minimum value or the minimum portion of the ball. That means I need to go to the bottom of the ball. So random position on the surface of the ball is the cost of the current values of the coefficients. Then the bottom of the ball is the cost of the best set of coefficients, the minimum of the function. So the goal is now to continue to try different values for the coefficients, evaluate their cost, and select new coefficients that have better, that means lower cost. So repeating this, you basically will lead to a bottom of the ball. So that is in general the overall approach that typically is part of the gradient descent algorithm. That means you are keep on iterating the different values, and so that this particular minimum is found, and our job is to actually find the minimum, which will be typically called as global minimum. So we can draw this like this. So where you basically have some values of m and b, because our equation was basically y is equal to mx plus b, and we need to find the minima. So we are basically, here we have plotted it with respect to m and b. So this is like a ball. So we start with some value. Typically people will start with 0 values. Then you change the m and b till you reach the minima. The error is minimum at the minima. You and use those values for prediction. So that is what actually the gradient descent algorithm does. So now the problem is, how do I reach the red dot? Suppose if I want to find the value of m and b both, because we require values of both m and b, because we don't know which is the best fit line. So that means I can have m1x plus b1, I can have m2x plus b2, like that I can have any value of m and b. So how do I basically go and find a minimum so that the MAC or that error that we are trying to is minimum? So you take a fixed size steps from the star to the dot. That means some value we start and then you keep on. However, the problem will be if I take a fixed step, then it will never reach the minimum. There is a chance, because you might miss that because we are taking a fixed size step. So what typically people will do is they will take a different size shape initially the step size will be larger and then it reduces, and they follow the curvature of the function. That means whatever the function, that graph is or that curve is, so they follow that. So at each point you basically find the slope, that means the tangent. So tangent gives the slope, and once you know the slope, we know the direction to follow, and then they will use something called as learning rate for the step adjustment. So here this is what the diagram can be shown. So you start with a higher or a larger step size, and then you keep on reducing or adjusting it till you reach the red dot, and the tangent can be found as the basically the each point as a basically the slope. So to do that, we know in mathematics to find the slope basically partial derivative is used. So I can, this is my equation and this is my cost function rather, and I want to basically minimize. So what do? I will take a partial derivative. So once I do del upon del m, so I am going to get an equation, and then similarly if I take del upon del b, I am going to get a value. So partial derivative gives me the slope. So this we know from our school mathematics or of 11th-12th standard or the first year engineering study. So once we know the slope, then we will use the learning rate to get the step. So typically people will calculate m, and it is an iterative process. So m, and there is some initial value of m minus the learning rate multiplied by the del upon del m, similarly del upon del b to calculate b. So that is in general the overall background with respect to the gradient descent. Now we will go into the complete mathematics which we have seen earlier, and then we will take it forward. When it comes to differentiation, we will first try to think from the perspective of a single variable differentiation. Then we will go towards vector, and then we will proceed it so that it applies to the matrices. So we have seen, as we have seen earlier also, like if I have an equation y is equal to fx, so essentially we are talking about a equation which is a basically a single variable equation. So if I have 2 points, so that essentially on a curve, then it is a secant. So that means if I want to compute del y by del x, then I am going to do f of x plus del x minus fx upon del x, and then as the limit del x tends to 0, then we are obtaining the tangent, and that is where I have explained you initially we need to find the slope or the tangent. So tangent is then the derivative of f at x. So in general we can write it as in terms of h also, as far as h goes, h is greater than 0. So the secant becomes tangent, and the derivative of f basically points in the direction of the steepest ascent of the f. So that is where the calculation of derivative is important, because it helps me to find the slope or the tangent. So once we know this concept, now if it's a polynomial, so if it is a polynomial of x to the power n, then I can always compute its derivative as n x to the power n minus 1. Again applying the same rules, we use the Taylor series and stuff like that, and we have done it as part of our mathematics in our engineering, probably as a first year engineering. So let's proceed now. So what are the different differentiation rules? So the differentiation rules are the product rule that we know, then the quotient rule, that means f upon gx, fx upon gx, and then the derivative of that, then the sum rule, that means fx plus gx and the derivative, and then the chain rule, which is a very important, because when we talk about the deep learning, we are going to compute the derivative, and then where we minimize, that means those derivatives has to be back propagated, and that's why the chaining is important, because chaining only helps me to back propagate the derivative of the error, that means the error between the truth and the predicted value. So that where I am using the loss function, so that error has to be propagated back, and that's where I require a chain rule. So the chain rule is basically given as g circle f denotes the function composition, that means the way in which from x I get fx, then I get g of fx. So the chain rule is, now if I apply a g of fx dash, then I am going to get g dash fx and then f dash x. So that is what basically this chain rule is highlighting here, and I am hovering the cursor. So this chain rule is very important, which we are going to apply later. So example is, now let us say if I have an equation h of x, which is 2x plus 1 whole to the power 4, then I can apply the chain rule as fx is 2x plus 1 and to the power 4 is f to the power 4. So if I apply the chain rule that we just have studied, then I am going to get the value answer as 8 of 8 of 2x plus 3. So this can be done on the paper. Okay, so that's the way I am going to compute derivative of hx using the chain rule. Then we'll try to understand little bit about partial differentiation and gradient. So gradient is essentially what? It's a generalization of derivative of function, derivative to function of several variables. So normally we use differentiation for a single variable, and if there are several variables, then we consider it as a gradient. So basically, to find a gradient of a function f with respect to x by varying one variable at a time and keeping the others fixed, so that is called as partial derivative. So gradient is what? It's a collection of partial derivatives. So that means I can have partial derivatives as grad f. So essentially it's a in the space of 1 by n, so it's a row vector, and it is and x is again a transpose, so it's a column vector. So this gradient is referred as Jacobian in the mathematics. So let's continue. So suppose if I just take an example of x plus 2y cube square, and if I want to find the partial derivative using the chain rule, now it's a two variable example, so I can always compute it, and we can see. So the gradient now will be the collection of del f upon del x1 and then del f upon del x2, and I can compute it using the chain rule. So the chain rule is a very important, and here now we can see df upon dx is essentially a vector of size 1 by 2, because there are two variables. So it's a one row vector and 1 by 2 columns. So what are the rules essentially? So to compute derivatives with respect to vectors in the space in dimension space, so gradients involve vectors and matrices. So we call these rules as, for example, the rules A for our understanding. So product rule, then the sum rule, and then the chain rule. Now chain rule is again very important. So del of del x of g circle f of x, so that means del of del x of g of fx we are going to do. So that means del g upon del f multiplied by del f upon del x. So that is essentially the chaining or chain rule. So applying chain rule, suppose if I want to apply the chain rule to two variables of x1 and x2, and x1 and x2 themselves are functions of t, then I can compute it like this. So del f upon del x1, then del f upon del x2, so this is the, and multiplied by del x1 upon del t, and then del x2 upon del t. So we can see it, if you just multiply this particular row to the column, then we can get it computation of gradient with respect to t. So that means f itself is a function of x1 and x2, and then x1 and x2 are themselves function of t. So some example. So here if I have x1 is sine of t and x2 is cos of t, then I can compute f of x1 and x2. Say this is the example. Then I can compute and just putting the chain rule. So again we are concentrating on the chain rule, because now here we are talking about the derivative of x1, that means del f upon del x1, then del x1 upon del x1 upon del t. Similarly del f upon del x2, and then del x2 upon del t. So if I now take it forward, then if x1 is a function of another one more variable, so s and t, and x2 is again a variable of s and t, then again I can compute using the chain rule, and I can get del f upon del s, and then similarly I can get del f upon del t. So then I can obtain the gradient by the matrix multiplication. So I can do this, and here now this particular thing del f upon del, it's now st. So it's a function of two variables instead of single variable which we are done earlier t. Now here we are talking about two variables. So now we are talking about a vector now, because now it will be so very clear. We started with x1 a function of t, x2 function of t, then we took it to st. So now we can think about a concept of gradient to vector valued functions. So that is vector field. So you have f which is n dimension, so essentially it will be mapped to m dimension. So for a function f, which will basically be where x is a vector, essentially x1 x2 xn, it's a n dimension in the map of n dimension. So corresponding vector of function values is given as fx is now composed, it's a f1x, f2x like that till fmx. So we are now generalizing the concept. So essentially it's a m dimension space. So differentiation rules for every fi are the same. However, the rules are going to be the same. So that means del f upon del xi is now del f1 upon del xi till del fm upon del x1. So essentially we are talking about the breaking the function into the multiple fi's, del fi's. So the vector valued function we are containing. So gradient of f is now df upon dx is essentially a rho. So df del fx upon del x1 till del fx upon del xn. So essentially we are now breaking it. So we are going to get a matrix. So the Jacobian is now a collection of all first order partial derivatives of vector valued function, because we are now talking about a vector valued function. The Jacobian is a m by n matrix. So that is what is very clear now. So chain rule, now we will apply chain rule. So suppose if I have a function, let's take an example, say fx is e to the power x1 into x2 square, and where x is now two values, that is x1 x2, and then gt is a t of cos t and t of sin t. So here we are talking about x1 is a t cos t and x2 is a t sin t, and we can compute dh upon dt as del f upon del x1 and then del f upon del x2, that means del f upon del x and del x upon del t. So here it's a del x1 upon del t and del x2 upon del t. So if you just do it, so we are going to get the value which is dh upon dt. We are applying the chain rule. So this completes our first portion of the presentation, where we have seen about the gradient descent and the how do we go about doing the how do we basically compute the gradients, and then we have considered it for the vector valued function. In the next part we will be taking up the remaining portion of the presentation. Thank you. Hi everyone. In the previous video, where we are trying to understand the gradients, the differentiation and stuff like that, so we have seen few things. In this video we will continue with respect to gradients and backpropagation, so that we understand it with respect to the neural network models. So in this presentation we are going to talk about gradients and then the backpropagation. So now let's try to understand the gradients of a least square loss in a linear model. So when it comes to machine learning, or for that matter the different activation function that we have seen as part of deep learning, one of them happens to be the linear function. So suppose if I consider a linear model, y is equal to phi theta, so it is of the form of basically y is equal to mx. So where now theta we are talking about in the d-dimensional space, and it's a parameter vector, then phi are basically the input features and it's n by d dimensional space, and y, which is going to be the output, are the corresponding observations, essentially we can say. So it's going to be in the space n dimension. So now we are going to define a function where we want to basically minimize the loss, and as we know there are several loss functions, and one of the loss function which is a very popular function is actually the least square function. So we can denote it as by L, say the loss function of E error. So there we are talking about the square of that term. That means when we are talking about the E theta, so essentially it's the subtraction from the observations, that means y minus phi theta. So that is actually the error, because whatever is the truth and whatever has been predicted or whatever is the current value, that difference is what is the error. Ideally, when we talk about machine learning model, or say when we talk about the deep learning, so essentially we are talking about the loss score, and that is where the importance of this error lies. So if I now want to basically comment on the dimensionality of the gradient, then I'm going to basically talk of del L by del theta. So that will be of 1 by d, that means it's going to be 1 by 1 cross d, that will be the dimension. So now we are going to apply the chain rule to compute the gradient. That means we want to compute del L upon del theta, and del L upon del theta is essentially del L upon del E multiplied by del E upon del theta. Now this we have seen as part of our previous presentation where we have seen about the chain rule that we have applied in various cases. So the dth element is given by del L upon del theta. Say it's essentially it's a 1 cross d. So the dth element will be 1 comma d, will be the summation of del L upon del E of the nth value, n is equal to 1 to whatever the max n, and then del E upon del theta n comma d. So that is what basically any particular dth element can be computed. Now we know that error square, because we are talking about the error square here, so it's a E transpose multiplied by E. So essentially when I want to compute del L upon del E, then I am going to get 2e to the 2e transpose. So again it's now going to be 1 by n dimension space. So del E upon del theta will be, now we are talking about this equation, so del E upon del theta will be minus phi, so that now will be n by d. So because now we are going to compute del L upon del E and then del E upon del theta. So now we have got those two things with us. So that means del L upon del theta will be minus 2 e to the power e transpose phi. So that means we can substitute those values. So you are going to get the result as shown in the screen, and which will be of the 1 by d space. So if I want to apply a chain rule, and essentially we are now talking about an L2 norm, because what we are doing is y minus phi theta, of that mod we are basically doing the square. So now we are talking about y minus phi theta transpose multiplied by y minus phi theta. So that is what the chain rule is going to yield me. Now let's try to understand the gradient of matrices. Now we are all doing this because we are slowly moving towards the backpropagation algorithm. So if I want to basically take gradient of matrices with respect to vectors, or for that matter other matrices, so we are going to get a multi-dimensional tensor, and we have seen how to use how we have used tensor in the previous videos. So tensor is what? Essentially it's a multi-dimensional array that collects the partial derivatives. So to compute the gradient of a matrix, say m by n matrix A with respect to p by q matrix say B, that means matrix A and matrix B. So these are the two matrices. So the resulting value, that is Jacobian, which we have seen earlier, it's a collection of that. So essentially is a 4-dimensional tensor. So the resulting Jacobian is m cross n cross or by p cross q. So those entries can be found by using Jij and then del Aij upon del Bal. So that is what essentially people will use this approach to calculate the gradient of matrices. Now let's proceed to the back propagation without going into too much mathematics about the matrices now. So in the machine learning and deep learning application, the model parameters are basically found by performing the gradient descent, and this we know because we have seen in previous videos where we have used this approach of gradient descent, the algorithm which we have called it as gradient descent. So Adam is one such this one example. So the gradient of, that is the gradient of learning objective with respect to the parameters of the model, that is what essentially we are now talking about. We want to calculate the gradient of learning objective with respect to the parameters of the model. So for a given objective function, we obtain the gradient with respect to the model parameters using calculus and then applying the chain rule. So here the implementation of the gradient itself can be significantly expensive than computing the function. Now this itself is a very interesting comment. So that's why so for training deep neural network model, the backpropagation algorithm, which is essentially given and has been basically improvised over a period of time, so starting from 1960 onward, so is an efficient way to compute the gradient of error with respect to the parameters of the model, because our job is now to consider that error which we just have seen. So the error, that is the truth, and the what we have predicted, so that is that error, so that with respect to the models of the parameter. So that is what basically we need to find as part of the overall approach, and that is where the backpropagation algorithm is an efficient way to compute the gradient. Otherwise the gradient itself computation will be significantly expensive than the calculating or computing the function. So gradients in a deep network. So the chain rule is used in deep learning, where the function value y is computed as many level function composition. So we have seen this as part of our chain rule, so where y is essentially what? So essentially it's a f of k is a function of f of k minus 1 till you keep on doing it till f of f1 of x. That is what we have seen when we have used it for two functions, that is g and f. So g of fx, that is what we have seen. So here, because in the deep learning you have the multiple layer and you basically are having the many level function composition, so this chain rule essentially helps me to provide that particular approach. So now here the x are the input. So for example, the input can be images. Then y are the observations, that means the labels, because if I have multiple images and I want to classify those images, then there will be labels corresponding to that those images. So the y's are essentially going to be the labels. So that means suppose if you have the images of say different vehicles, say car, bicycle, then two-wheeler, say bike, then scooter, like that, or say for example you have various four-wheelers like car, truck, bus, like that. So you need to make a decision whether the particular vehicle is a car or whether it is a truck or whether it is a bus, like that. So that means x are going to be the input images, then y are the observations, that is the class label, and then the function that we are going to use or that will be there, which basically is a fi for I is equal to 1 to k. So it possesses its own parameters. So when it comes to now neural network, where we are basically having multiple layers, a particular ith layer function is given by f of I of x of I minus 1. So that particular thing is a activation function. So this we have seen as part of our basic understanding of the neural network model. So where essentially it's a dot product of a of a and then the x, so that we have seen, plus the b is the bias. So x of I minus 1 is the output of the previous layer, then the sigma is the activation function, and the various activation functions can be linear function or the logistic sigmoid or ReLU or tanh and all that. So all those things we have used as part of the working with the deep learning. So to train the model, you basically require gradient of a loss function L with respect to the model parameters AI and Bj for j is equal to 1 to k. So gradient of L with respect to the inputs of each layer is what you require, that is gradient of a loss function and the gradient of L with respect to the inputs of each layer. So these are the essentially the two things that we are talking about. Now this is the diagram that is actually showing the forward pass, where you have the input x and then you have this parameters which are the model parameters as AB, and then the and then it is basically
it's in the forward pass. So the network structure with inputs x and the observations y. So f0, so essentially we are talking about the x, which is when we talk about f1, f2, so f0 is actually the input, and then any fi is basically the activation function, then the ai fi minus 1 plus bi, and for I is equal to 1 to k. So this is the in general the network structure when we talk about the deep network or a neural network. So to find the AIBJ, that is what essentially you require, because these are the parameters which actually control or govern the behavior of the layer. So to find AIBJ, that is AJBJ, we want to, that is the aim for j is equal to 0 to k minus 1, such that the squared loss is minimized. So that means we have seen this y minus f of k theta comma x, because x is the input and theta is basically a0 b0 like that till a of k minus 1 till bk. So to obtain the gradients with respect to theta, we are going to find the partial derivatives of L with respect to parameter theta j, which is essentially ajbj for each of the layer. Then we can use the chain rule. So if I use the chain rule on this, so I can compute del L upon del theta k minus 1. So you are going to get del L upon del fk, then multiplied by del fk upon del theta k minus 1. So like that, if you keep on doing, so essentially what you get is, you get the terms which are marked in orange color here are the partial derivatives of the output of a layer with respect to input. Why? Because fk is the output, then fk minus 1 is the input, like that, or and initially x0 or the f0 is essentially the x. So orange terms are the partial derivative of output of a layer with respect to input. The blue terms are the partial derivatives of the output of a layer with respect to its parameters. Now the parameters are basically theta, and theta is essentially aj comma bj, because these are the parameters that are used to model or to modulate the behavior of the of a particular layer. So essentially when we talk about now the backward pass, so now you have this other way of putting it. So that means now you have to propagate the thing. So back propagation is what? It's essentially the technique to numerically evaluate the gradient of a function by working with the intermediate variables and applying the chain rule. So that is what we have seen this earlier. So back propagation is a technique to numerically evaluate the gradient of a function, and gradient of a function is essentially we are computing the loss function with the intermediate variables and applying the chain rule, and we have seen various structures of neural network. So here the figure is showing the gradients that are passed backwards through the network. So we can see here this figure is basically those gradients are shown as a red one, which are passed backward through the network. So let us take a graph now. So here we have this input x. So with the flow of data from x to y via some intermediate variable, say a to b, a and b. So if I want to compute dy upon dx by applying the chain rule, the way in which I am going to compute is dy upon dv, then dv upon da and da upon dx. So this we now know. So we know the associative property of matrix, which we have seen as part of our mathematics learning probably in the first year of engineering. So for any three matrices A, B, C, so in bracket say A star B, and the bracket complete multiplied by C is essentially is equal to A star multiplied by B star C. So just to put it in a generalized way, if A is an M by P matrix and B is a P by Q matrix, and C is a Q by N matrix, so here we can see we are taking care of P and then Q is met. So then A in bracket BC is equal to AB in bracket AB and then C. So this is actually called as associative property of matrix multiplication. So using this associative property of matrix multiplication, we get two options. So what is that option? One is dy upon dv, and then dv upon da, and then da upon dx. This is the first option. Second option is dy upon dx is equal to dy upon dv multiplied by dv upon da
and then dA upon dx. So here what we are done is basically the bracket is actually changed. That's what basically. So A in bracket BC is equal to AB multiplied by C. So this is what we have seen as part of the associative property. So that means the first option is called as reverse mode, because the gradients are propagated backward through the graph, that is reverse to the data flow. And the option 2 is actually the forward mode, because the gradients flow with the data from left to right through the graph. So that is what we have basically seen as part of this video, or this particular diagram, that the backward pass and then the forward pass. So here this was the forward pass where we have seen, so from f0 we have basically sent it till fk. So this was the forward pass, and this diagram where we have seen, so the gradients are passed backward through the network. So that means this is the final loss function which we have seen as part of overall structure of deep learning. So here this error is basically what, it's a technique to numerically evaluate the gradient of a function by working the intermediate variables and applying the chain rule. That means we want to propagate the basically the gradient. So that is what we have seen. So one is a reverse mode, and the option 1 is a reverse mode, and the option 2 is a forward mode. So let's continue. So in neural network, the input dimensionality is much higher than the dimensionality of the label. That is fine, because if I have multiple images, then images itself is a I can have 2 dimension. Then in the images itself could be a color images, or a black and white images, or I can have a video. However, I will be, as a dimensionality of the label probably will be only like just one vector, or a one basically, like we are classifying multiple images, so the answer will be like you have a car, or whether it is a bus or something. So that means the dimensionality of the input image is, or the input is much higher than the dimensionality of the label. So example of reverse mode computation. So let us say that the function is some very complex function, x square plus e to the power x square plus cos of this, so like that. So we can use the intermediate variable. Suppose if I decide to write a C program, or a normal basic some simple program, so I will use, say, a is equal to x square, then b is equal to e to the power x exponential of a. So like that we keep on doing in a multiple variable. So that means it's a intermediate variable. So computation graph showing flow of data and the computation required to obtain f will be like, from x you compute x square, then you basically get a, then you find the exponent, then you get b, then you add it, so that you get a plus b, then you basically have a c, then you take a root of that, so you basically get d. Similarly you compute cos, so you get e, then you add, and then you finally get f. So that is the way this particular equation, or this particular equation can be considered if I, or can be imagined if I want to write a program using the intermediate variables. So computing the derivatives of the intermediate variable, so I am going to compute so del a upon del x, so which is going to give me 2x, then del b upon del a is going to give me e to the power that is exponent e a. Like that I am going to compute del c upon del a, del d upon del c, then del e upon del c, like that. Why? Because this is my diagram, so I am going to compute derivatives of the intermediate variable. From the graph, if I want to compute del f upon del x, so by working backwards from the output, and then that means from the output and applying chain rule, I am going to get del f upon del c, so this is the first place, then del f upon del b, then del f upon del a, and then del f upon del x. So that is what basically from the graph I am interested in computing. So that means del f upon del c is a combination of del f upon del d, and then del f upon and del d upon del c, like that we can see in the slide. So all those details are worked out. So since I now have computed all those derivatives individually, so I can compute del f upon del x. So del f upon del x, if I just substitute it, I am going to get, finally answer will be something like basically del f upon del c will be this, and then all those things if I just compute here one by one, so I am going to get del f upon del x is what I am basically. So by substituting values of derivatives, of intermediate variables, I can get del f upon del x. So the point here is actually what? So summarizing, so computation required for calculating the derivative is of similar complexity as the computation of function itself. So this is a very important understanding. Otherwise, computation of derivative itself would have been a very complex task. The mathematical expression for the derivative is df upon dx, significantly more complicated than the mathematical expression of the function fx. Reverse mode is computationally significantly cheaper than the forward mode. So this is a very interesting observation that we have seen. So we can generalize now. So suppose if I have a input variables x1, xd t with the input variables of the function, and then xd plus 1 to xd minus 1, say capital D, with the intermediate variables, and xd the output variable. So then if I want to compute, then the computation graph can be expressed as d plus 1 till d, and xi is gi of xpa of xi. That means this is equation 1. So where gi is the elementary function and xpa are the parent nodes of the variable xi in the graph. So we can use a chain rule to compute the derivative of the function. So by definition, the final f will be the xd because that is the final one. So del f upon del xd will be 1. So this is very simple. So for other variables, we compute using the equation, which is the equation 2. So del f upon del xi is going to be given by the equation that is given in the slide. So where, and here we are talking about Pa is the set of parent nodes of xi in the computation graph. So overall we can see the generalizing the back propagation. So equation 1 is the forward propagation of a function, and equation 2 is the back propagation of the gradient through computation graph. So here we can see this is the equation 1. We are talking about d plus 1, and we are talking about till d xi is gi upon. So this is the equation 1, and this is the equation 2. So equation 1 is the forward propagation of a function, and equation 2 is the back propagation of the gradient through computation graph. So for neural network training, the error of the prediction with respect to the label is back propagated. So that we know, that is what where we are computing the error with respect to the prediction. So that's what I used to tell. And then the differentiation approach works whenever we have a function that can be expressed as a computation graph where the elementary functions are differentiable. So this basically completes the overall understanding of the backpropagation algorithm and why the derivative chaining is important, and the basics about the mathematics related to the derivative differentiation and then the partial differentiation. So thank you.